Turning cornmeal into Cheetos takes insane heat and non-stop precision. Inside massive factories, raw ingredients are blasted through high-powered extruders, coated in iconic cheese dust, and bagged by the millions every single day. In this documentary, we take you behind the scenes of the Cheetos production line, where fiery machines and rapid-fire automation keep the crunch coming. The production of Cheetos begins not with cheese or seasoning, but with one humble ingredient: corn. In fact, the specific type of corn used in Cheetos manufacturing is carefully selected and processed to meet exacting technical standards before it even enters the plant. The base product of every Cheeto is degermed cornmeal, derived from a variety of field corn that is specially cultivated for its high starch content and low fat levels. This corn must produce a uniform, predictable puff when subjected to extreme heat and pressure, so its density, moisture content, and kernel hardness are closely monitored even at the agricultural stage. Farmers contracted by the manufacturer are required to meet tight tolerances in grain quality, harvesting methods, and post-harvest drying to ensure the raw corn will meet the standards for industrial puffed snack production. Once harvested and transported to the ingredient supplier, the corn undergoes an initial cleaning to remove plant debris, soil, and foreign materials. It is then taken through a degermination process, in which the outer bran layer and the germ, the oil-rich, nutrient-dense part of the corn kernel, are removed. This step is essential. While germ and bran contain healthy fats and proteins, their presence can negatively impact the expansion properties and shelf life of the final product. Germ oil can go rancid over time and interfere with the consistent puff structure that defines a Cheeto. What remains after degermination is the starchy endosperm, milled down into a fine cornmeal that becomes the building block of every puff. This cornmeal is then enriched with a blend of vitamins and minerals, including riboflavin, niacin, iron, and folic acid. The enrichment not only helps meet nutritional labeling requirements, but also contributes to uniformity in the extrusion process, as these additives influence how the mixture reacts under heat and pressure. The resulting product is a dry, golden yellow flour with a specific granulation profile tailored to the plant's extrusion parameters. Before it is used on the production line, the cornmeal is stored in temperature and humidity-controlled silos directly connected to the processing plant. These silos often hold hundreds of metric tons of product and are designed to keep the cornmeal in a stable state for extended periods. Pneumatic systems transfer the cornmeal through stainless steel pipelines to weigh hoppers on the factory floor, where batch sizes are precisely measured. Real-time inventory sensors track the flow of material and communicate with the factory's central control system to automatically replenish supply lines as needed, ensuring uninterrupted production. Now it's time for the first transformation phase: hydration and preconditioning. The cornmeal is metered into a continuous mixing system where it is blended with water or steam to raise its moisture content to a narrowly specified range, usually between 15% and 20%. This step is essential to prepare the starch molecules for gelatinization. The equipment used here is not unlike a ribbon blender or paddle mixer, which agitates the mixture thoroughly to ensure every granule of cornmeal is evenly hydrated. Water is introduced through atomizing nozzles positioned at calculated intervals along the mixer's length, and multiple moisture sensors along the pathway feed back to the PLC system to adjust water input in real time. This moist mixture, often referred to as dough, despite its loose, crumbly texture, is held briefly in a conditioning tank to allow for even moisture distribution. The temperature and residence time are carefully controlled. If the mix is too hot or too wet, it may pre-gelatinize and clog the extruder. Too dry, and it won't expand properly. During this stage, the product is slowly moved along a jacketed screw conveyor that maintains a consistent temperature and prevents clumping. Now we arrive at the heart of the production line, the extruder. Industrial Cheetos are made using a twin-screw extruder, one of the most sophisticated and critical machines in the plant. The twin-screw configuration allows for highly controlled processing of the corn mixture, providing better mixing, higher shear, and superior control over temperature and pressure compared to single-screw models. The hydrated cornmeal is fed into the extruder barrel, where it encounters two rotating screws that convey the material forward under intense mechanical pressure. External heaters line the barrel and raise the temperature incrementally as the product moves through each zone. Inside, shear forces generated by the screws convert some of this mechanical energy into heat, further increasing the temperature of the dough. The intense conditions inside the extruder, pressure in the range of 200 to 500 psi, and temperatures from 130 degrees Celsius to 180 degrees Celsius, cause the starches in the cornmeal to gelatinize and the water to superheat. The dough undergoes plasticization, becoming a molten mass under pressure. As this molten dough reaches the end of the barrel, it is forced through a die, the precision-crafted metal plate that defines the shape of the puff. The die hole is round and small, but as the dough exits into atmospheric pressure, the superheated water in the mixture flashes into steam, causing the structure to puff and expand dramatically in a fraction of a second. This rapid expansion is responsible for the iconic airy texture of a Cheeto. Just outside the die, rotating knives spin at high speed, slicing the continuous stream of puff into uniformly sized segments. The speed of the knives determines the length of the puff, while the pressure and temperature within the extruder affect its diameter and density. But even after this high-tech transformation, the newly extruded Cheetos are far from finished. They are still pale, moist, and bland, essentially unseasoned corn puffs. The next stage is all about turning them into the crunchy, craveable snack that consumers instantly recognize. First, the extruded pieces are conveyed via vibrating trays to a frying system. Here, they're submerged in hot oil, typically corn or canola oil, at carefully controlled temperatures ranging between 160 degrees Celsius and 180 degrees Celsius. The residence time in the fryer is only about 20 to 40 seconds, but in that time, the moisture content is reduced dramatically from around 15% to under 2%. This not only creates the final crispy texture, but also deepens the color slightly, giving the snack its characteristic golden hue. The fryer itself is a marvel of engineering, equipped with multiple sensors and filtration systems. Oil turnover rates are high, meaning that fresh oil is constantly added, while spent oil is removed and filtered to maintain quality. Skimmers remove any floating particles, and oil chemistry is monitored for signs of oxidation, free fatty acid levels, and polymerization. If any readings fall outside of the strict parameters, the fryer automatically triggers corrective actions, dosing with fresh oil, increasing filtration, or even pausing the line to prevent compromised batches from continuing downstream. After exiting the fryer, the Cheetos are carried on mesh conveyors through an air cooling tunnel. High-powered fans blow ambient or conditioned air over the freshly fried snacks, bringing them to a safe handling temperature and ensuring any surface oil solidifies just slightly to help the seasoning adhere. These cooling conveyors are extended and designed with soft vibratory motion to prevent breakage, ensuring that the delicate puffs remain intact before entering the seasoning phase. Next, the Cheetos are transferred into a massive rotating flavor drum, where their bland exterior is transformed by a shower of powdered cheese blend. But before we dive into the complexities of seasoning, we'll need to explore how oil coating is applied for adhesion and how powder distribution systems are calibrated to ensure every single puff gets the perfect amount of flavoring. This next part of the production process is where precision meets sensory science, and the result is the addictively cheesy snack that has become a global favorite. Now it's time to dive into one of the most iconic and intricate stages in Cheetos manufacturing. The flavoring phase. This is where the bland, puffed, and fried corn kernels are transformed into the intensely savory, cheese-coated snacks recognized all over the world. The process of seasoning Cheetos is not merely about tossing on a bit of cheese powder. It is an engineered, tightly controlled operation that determines product consistency, taste balance, visual appeal, and even mouthfeel. Everything from the size and porosity of the puff to the electrostatic charge of the powder particles is taken into account in this phase. After exiting the cooling conveyor from the fryer, the puffs are transferred into large rotating cylindrical drums called flavor tumblers. These drums are typically positioned on a gentle incline and rotate slowly, creating a continuous cascade of puffs inside the drum that exposes every surface area of each piece as they tumble forward. This mechanical tumbling is crucial. It ensures an even coating without crushing the fragile, aerated product. Inside the drum, two key applications occur almost simultaneously. First, a fine mist of oil is sprayed onto the hot puffs. Then, a controlled stream of seasoning powder is dispensed over the tumbling mass. The oil, which is typically a neutral vegetable oil like corn or canola, plays several roles in this step. Primarily, it acts as an adhesive layer that allows the seasoning powder to stick effectively to the puff's surface. Additionally, it helps activate the flavor compounds in the powder blend, carrying volatile aroma molecules and enhancing taste perception. The oil spray system uses ultra-fine atomizing nozzles that are precisely calibrated to deliver a uniform coat without oversaturation. Too much oil, and the puffs become greasy and soggy. Too little, and the powder won't adhere properly, leading to uneven seasoning distribution and flavorless bites. The timing, angle, and rate of oil application are closely monitored and adjusted by sensors and programmable logic controllers. Real-time feedback systems measure oil usage, droplet size, and the thermal signature of the puffs to ensure that coating is optimal under varying production speeds or ambient conditions. This level of automation ensures consistency across thousands of pounds of product produced per hour. As the puffs are coated in oil, the seasoning powder is introduced using a vibratory feeder or screw conveyor system. The powder is held in a hopper mounted above the flavor drum and is dispensed through controlled openings at a fixed rate, matched to the flow of puffs. The exact dosing rate depends on the type of Cheetos being produced. Flamin' Hot varieties require slightly more powder per unit than the traditional cheese puffs due to differences in density, powder, granularity, and flavor intensity. The seasoning blend itself is a complex formulation engineered not only for taste, but also for flow characteristics, adhesion, and shelf stability. The base of the powder is often dehydrated cheddar cheese, spray-dried into a fine particle form. This is combined with whey or whey protein concentrate, maltodextrin, salt, monosodium glutamate, MSG, disodium phosphate, citric acid, and natural or artificial flavors. Each of these ingredients plays a very specific role. Maltodextrin, for example, acts as a carrier and anti-caking agent that helps the powder distribute evenly and resist clumping. Citric acid provides a tangy bite that enhances cheese flavor. MSG boosts umami and deepens savory perception. Color additives like annatto or oleoresin paprika for classic cheese and red 40 or yellow 6 for Flamin' Hot are oil dispersible pigments that give the snack its vivid appearance without creating spotting or streaks. The particle size distribution of the powder is engineered to align with the surface texture of the puffed snack. Powder that's too coarse will fall off, and powder that's too fine will clump or create an overly dusty texture. To prevent powder fallout, electrostatic systems are sometimes used in high-speed lines. In these cases, the powder is given a minor static charge to improve its affinity for the puff surface, minimizing waste and improving adhesion. Inside the flavor tumbler, the balance of oil spray and powder distribution creates a beautiful, uniform layer of seasoning that fully coats each puff without pooling at the bottom of the drum or leaving bald spots on the product. The drum's internal design is key. Angled baffles gently lift and drop the puffs to keep them moving without subjecting them to mechanical stress. As the snacks make their way to the end of the drum, they are now visually and sensorially transformed. Bright orange, evenly coated, and bursting with aroma. Once the seasoning phase is complete, the fully flavored Cheetos are gently transitioned to the final conveyor belt systems that lead to the packaging area. Here, another series of quality control measures come into play. Inline camera systems inspect color uniformity and powder coverage using advanced image recognition algorithms. If a section of the product stream is detected to have an irregular appearance, whether due to light seasoning, overcoating, or discoloration, it is flagged and diverted from the main line for manual inspection or disposal. At this point, the Cheetos are still vulnerable to moisture pickup, oxidation, and mechanical damage, so the packaging process must move swiftly and with precision. The conveyor system delivers the finished puffs to a multi-head weigher mounted above the bagging machines. This machine uses multiple weigh hoppers to rapidly measure exact product portions, typically in the range of 28 g to 250 g per serving, depending on the bag size. These weighers use real-time load cell feedback to select the optimal combination of buckets to match the target weight, within a tolerance as tight as +2G. Each pre-measured portion is released down a chute into a vertical form-fill seal (VFFS) machine. These machines work by pulling a flat roll of pre-printed film through a collar that forms it into a tube. The bottom of the tube is heat sealed to create the first seam, the Cheetos are dropped in, and then the top is sealed and cut, simultaneously forming the bottom seal of the next bag in line. These machines can fill and seal over 100 bags per minute per lane, and multiple lanes often run in parallel for large-scale production. The film used for the packaging is multi-layered and engineered to provide barrier protection against light, oxygen, and moisture. It typically includes an outer polyester film for print quality and visual appeal, a middle layer of aluminum or metallized polypropylene for oxygen and light resistance, and an inner polyethylene layer for heat sealing and moisture resistance. As each bag is sealed, a date code, batch number, and factory identifier are printed using high-speed inkjet printers for traceability. Just after sealing, every bag passes through a series of checkpoints. Metal detectors scan for any foreign objects, vision systems verify print alignment and code readability, and weight checkers ensure compliance with regulatory standards. Non-conforming bags are automatically ejected onto a rejection conveyor, where they are set aside for manual inspection. Approved bags are then grouped and packed into cardboard shipping cartons by robotic pick-and-place systems or automated drop packers. These cartons are sealed, barcoded, and routed to the palletizing station. Here, industrial robotic arms stack the cartons onto wooden or plastic pallets using optimized patterns for stability and load balance. As each pallet is completed, it is wrapped in stretch film to secure the load and protect it from dust and humidity during storage and transportation. The palletized loads are then scanned into the plant's warehouse management system, which tracks location, batch status, and distribution destination. Some pallets are moved to ambient storage if they are designated for short-haul routes, while others are transported to climate-controlled storage areas that maintain low humidity and consistent temperatures, ensuring that the product maintains its texture and flavor until it reaches its final destination. What follows is the outbound logistics phase, where the pallets are loaded onto trucks, routed to distribution centers, and delivered to retailers. But for now, every step inside the production facility, from the moment the cornmeal is hydrated to the final bag, passing the last inspection point, has been a meticulously engineered series of chemical, mechanical, and sensory transformations. Every component of the Cheetos production line is designed not just for efficiency and speed, but to deliver a reliably indulgent experience in every bag. And it all happens in a continuous, automated, high-output environment that must maintain exacting standards of quality, cleanliness, and consistency hour after hour, shift after shift. One of the key operational pillars at this stage is environmental control. Temperature, humidity, and airflow within the production zones are tightly monitored and controlled around the clock. Cheetos, especially after frying and seasoning, are highly sensitive to ambient conditions. If the air in the seasoning or packaging area carries too much humidity, for instance, the cheese powder may begin to clump, reducing its dispersibility and leading to uneven coating. Worse still, excess moisture can cause the puffs to begin absorbing water from the air, softening the texture and compromising the crisp, dry bite expected by consumers. To prevent these issues, HVAC systems specifically engineered for food processing environments are deployed throughout the Cheetos plant. These systems do more than just heat or cool. They dehumidify, filter, and exchange the air in sensitive zones at rapid intervals, ensuring a constant flow of purified, dry, temperature-stabilized air. Some areas, such as the seasoning tumblers or the vertical form-fill seal zone, may be isolated with positive air pressure to ensure that external air, dust, and contaminants do not seep into these critical zones. These environmental systems are integrated with digital controls that feed data into the facility's central monitoring hub. Temperature and humidity data are tracked every few seconds, and if any reading moves outside of pre-programmed tolerances, automatic alarms notify technicians to investigate immediately. In some cases, the system will even halt upstream processes automatically to prevent production under unsuitable conditions, protecting product quality. While environmental controls maintain external conditions, another system ensures the quality of what's happening on the line, inline quality assurance, and real-time analytics. Throughout the Cheetos line, from extrusion to bagging, dozens of sensors, scanners, and cameras work in unison to gather data on key quality metrics. These include moisture content, oil absorption rate, puff size, color uniformity, seasoning coverage, and weight per unit. Each of these factors contributes not only to taste and mouthfeel, but to customer satisfaction and regulatory compliance. Advanced laser micrometers and stereo imaging cameras measure the dimensions of each puff as it moves across the line at high speed. If puffs fall outside the programmed size range, either due to inconsistent extrusion pressure, die blockage, or improper cutting, those units are flagged and rejected automatically using pneumatic diverting arms. Simultaneously, optical sensors inspect the color of the fried puff to confirm it matches brand-specific targets. Color variation could indicate improper frying time, fluctuating oil temperature, or oil degradation. The system will trigger alerts or shut down sections of the line if it detects drift from acceptable limits. Another important part of inline quality is the metal detection system. Every snack must pass through high-sensitivity metal detectors or, in some cases, X-ray systems just before packaging. These devices scan for trace amounts of ferrous, non-ferrous, and stainless steel contaminants which could originate from worn machinery parts, upstream, or during maintenance. The sensitivity of these machines is such that they can detect metallic particles smaller than a millimeter in diameter. If a contaminated bag is identified, it is automatically ejected from the line, recorded in a digital log, and sent for root cause analysis. In high-output snack manufacturing, product changeovers are another critical concern. A single plant might produce multiple Cheetos variants: classic cheese, flamin' hot, jalapeno cheddar, and limited editions on the same line, sometimes switching several times per day. To avoid cross-contamination of flavor profiles and allergens, the factory must execute a full product changeover, which includes both physical and procedural steps. The final bags of one variant are run through the line until the seasoning and product types are completely cleared. Following that, dry cleaning and wipe down protocols are enacted on exposed surfaces. In flavor tumbler zones and powder feeding systems, residue removal is handled by a combination of mechanical vacuums, compressed air nozzles, and in some cases, wet cleaning cycles. Pipes carrying seasoning powder are often disassembled and cleaned manually or flushed with air-driven pigs, foam or rubber projectiles that scrape the interior of the tube clean as they are propelled by compressed air. All cleaning steps are verified through ATP, adenosine triphosphate, swab tests or allergen-specific strip tests to confirm the line is ready for the next product. Equipment cleaning and sanitization extend far beyond changeovers. Each section of the production line is scheduled for deep cleaning on a regular basis, with some components cleaned daily, others weekly, and critical systems, like oil fryers, undergoing monthly shutdowns for intensive maintenance. Every cleaning task is documented in a digital sanitation log that includes time-stamped photos, chemical usage records, technician ID, and verification by a supervisor. This log ensures compliance with food safety regulations and internal auditing systems. Speaking of oil fryers, one of the more maintenance-intensive systems in the Cheetos plant is the oil management setup. Used frying oil is constantly cycled through multi-stage filtration systems that remove fine particulates and oxidized residues. Inline sensors monitor oil color, free fatty acid content, and total polar compounds, all indicators of oil degradation. When thresholds are approached, fresh oil is introduced, and a portion of the old oil is purged to waste recovery tanks. This spent oil is not discarded haphazardly. Instead, it is captured and sent to third-party processors who refine it for use in biodiesel production or industrial lubricants, creating a closed-loop waste management process that supports sustainability goals. Seasoning systems have their own challenges in terms of dust and waste control. Cheese powder and spice blends are notoriously airborne, so extraction hoods fitted with HEPA filters are positioned above tumblers and conveyors to capture stray particles. These systems not only keep the air clean for workers, but also prevent buildup on surfaces and reduce cross-contamination risk. Powder recovered in this way is not reused in production, but is collected and weighed for waste tracking. Many factories monitor seasoning powder yield versus usage to optimize application and reduce excess without compromising flavor intensity. Additionally, factories employ floor-level waste segregation systems, where organic waste, such as broken puffs or overcooked batches, is separated from packaging materials and cleaning byproducts. Organic snack waste is often sent to animal feed processing plants or used in anaerobic digesters to generate energy, while plastics are compacted and shipped to recycling partners. These systems not only reduce landfill usage, but also lower the facility's total environmental impact per unit of product. Every phase of the factory's operation is governed by a robust system of documentation and auditing. Real-time production data is logged into the Manufacturing Execution System, MES, which connects to the plant's Enterprise Resource Planning, ERP, platform. This system allows plant managers to track every batch of Cheetos from cornmeal input to palletized output. If a quality issue is flagged post-distribution, every input, cornmeal batch, oil lot, seasoning blend, even the operator ID can be traced within seconds. This level of transparency is essential for large brands that operate under continuous scrutiny from regulators, retailers, and consumers alike. All these systems, from the air handlers and fryers to the conveyors and flavor blenders, are monitored by a central control room staffed by trained process engineers and operators. The control room acts as the nerve center of the factory. Touchscreen interfaces display real-time data on line performance, yield percentages, waste figures, and energy usage. Alarms and alerts notify the team of any deviation in pressure, temperature, fill levels, or machine health. The staff can make remote adjustments, schedule maintenance tasks, and even initiate partial or full shutdowns directly from their stations. In many facilities, predictive analytics platforms are integrated into these systems. Using machine learning algorithms, these platforms analyze historical and current data to forecast when a component might fail, how yield might shift under ambient changes, or what impact a change in oil temperature might have on puff expansion. This allows for proactive decision-making, reducing downtime and maximizing efficiency. The manufacturing of Pringles is an intricate process that combines food science, precise engineering, and large-scale automation to produce the uniform, crisp, and stackable potato chips recognized worldwide. Unlike traditional potato chips, which are sliced from whole potatoes and fried, Pringles are created from a specially formulated dough made primarily of dehydrated potato flakes, starches, and seasonings. The process of making Pringles in a factory involves several key stages, each meticulously designed to ensure the final product meets strict quality standards. It all begins with selecting the right raw ingredients, primarily potatoes, which serve as the foundation of the chips. However, not just any potatoes will do. Pringles require specific varieties with the right starch content to achieve the desired texture. High starch potatoes are preferred because they contribute to the crispness of the final chip and help bind the dough together during production. Once the right potatoes are sourced, they are transported in bulk to the factory, where they undergo an initial round of inspection. Before entering the processing phase, the potatoes are stored in climate-controlled environments to maintain their quality. Even small variations in temperature and humidity can affect their starch content, which in turn impacts the final texture of the chip. Workers constantly monitor these storage conditions to ensure that the potatoes remain in an optimal state before processing. When ready for use, the potatoes are moved to the preparation area, where they go through a rigorous washing process. Large industrial washers, equipped with rotating brushes and high-pressure water jets, remove dirt, debris, and any residual pesticides from the potato skins. This step is crucial, as any impurities at this stage could compromise the quality of the final product. The washing process is thorough, ensuring that only the cleanest potatoes make it to the next stage. Once cleaned, the potatoes are sent through a peeling machine, which uses either steam or mechanical abrasion to remove the skins efficiently. Steam peeling is a common method in large-scale food production, as it allows for quick and uniform removal of the skin with minimal waste. The peeled potatoes are then conveyed to slicing machines, but unlike conventional potato chips, where these slices would be fried, the goal here is to break them down into a form that can be processed into a dough. To achieve this, the sliced potatoes are sent through a pre-cooking stage, where they are partially heated to help break down their cellular structure. This step makes it easier to remove moisture later in the process. The pre-cooked potato slices are then transferred to large industrial dryers, where hot air circulates around them, slowly extracting moisture until they are fully dehydrated. What remains after this process is not whole potato slices, but thin, brittle flakes of potato. These dehydrated potato flakes serve as the primary base for Pringles and are stored in large silos within the factory. However, potato flakes alone are not enough to form the distinctive shape and texture of Pringles. Additional ingredients must be added to create the dough that will eventually be shaped into chips. When it is time to begin the production of a batch, the potato flakes are carefully measured and transferred to industrial mixing machines. Inside these massive mixers, the flakes are combined with other ingredients such as cornstarch, wheat starch, emulsifiers, and small amounts of salt and sugar. These additional ingredients help give Pringles their characteristic crunch and structure while also ensuring that the dough is flexible enough to be shaped without crumbling. Water is then gradually added to the dry mixture, and the entire batch is kneaded until it forms a smooth, pliable dough. This step is one of the most crucial in the entire process, as the consistency of the dough determines how well the chips will hold their shape and how they will fry later in the process. Too much water and the dough will be too soft, making it difficult to handle. Too little and it will become too dry, leading to chips that may crack or break during production. The mixing process is highly automated, with computer-controlled machines ensuring that every batch has the same precise ratio of ingredients. Factories use real-time monitoring systems to adjust the moisture content and consistency of the dough as needed, ensuring uniformity across millions of chips. Any slight variation in dough quality could lead to a final product that does not meet the brand's strict standards, so maintaining precise control over this step is critical. Once the dough reaches the perfect consistency, it is ready to be shaped. However, before this can happen, the dough must be processed into thin sheets. This is accomplished using large industrial rollers, which gradually flatten the dough to an exact thickness. The thickness of the dough sheet is critical, as it determines the final texture and crunch of the Pringles. If the dough is too thick, the chips will be too hard. If it is too thin, they may become fragile and brittle. The flattened dough sheet is then conveyed to a cutting station, where specially designed rotary cutters stamp out individual chip shapes. Unlike traditional potato chips, which take on random forms based on how they are sliced, Pringles are designed to be identical in size and shape. Each cutter is engineered to create the precise oval form that allows the chips to stack perfectly inside their cans. During this process, any excess dough that remains after the chips are stamped out is collected and fed back into the mixing stage. This recycling process minimizes waste and ensures that as much of the raw material as possible is used efficiently. The ability to reuse excess dough is one of the advantages of making Pringles from a formulated dough rather than whole potato slices. At this point, the chips are still in their raw, unbaked form. They have been cut into shape, but they are not yet crispy. To achieve their signature texture, they must go through the next phase of the manufacturing process, where they will be carefully molded and cooked. This is where Pringles truly begin to take on their distinctive identity. Before they can be cooked, the raw chips must be shaped into their famous curved form. This is done using a specialized conveyor system that gently places each chip into a custom mold. These molds are designed to hold the chips in a precise curve, known as a hyperbolic paraboloid, which is what gives Pringles their unique stacking ability. The shape is not just for aesthetics. It also helps distribute weight evenly when the chips are stacked in their can, preventing them from breaking easily. Once placed in the molds, the chips are conveyed toward the cooking stage, where they will be exposed to controlled heat and oil. This step is critical in achieving the crispy, golden brown texture that Pringles are known for. However, unlike traditional potato chips, which are deep fried in vats of hot oil, Pringles are cooked in a specialized method that ensures even frying while maintaining their precise shape. At this point, the chips are not yet fully cooked, nor have they been seasoned. The next phase will involve exposing them to heat and oil, followed by a careful seasoning process that gives each chip its final flavor. But before that happens, factory workers and automated quality control systems continuously monitor the process to ensure that each chip is perfectly shaped and free of defects. With the raw dough pieces now cut into their precise, uniform shapes and carefully placed into their curved molds, they are ready to undergo the critical cooking process. This step is what transforms the soft, pliable dough into the crisp, golden brown chips that Pringles are known for. Unlike traditional potato chips that are submerged in deep vats of hot oil and fried freely, Pringles undergo a much more controlled cooking method to maintain their exact shape and texture. The chips, still nestled in their curved molds, travel along a continuous conveyor belt into an industrial fryer. This fryer is designed to ensure that each chip is cooked at an exact temperature for a precise amount of time. The temperature inside the fryer is meticulously controlled, typically ranging between 300 degrees Fahrenheit and 375 degrees Fahrenheit, depending on the specific requirements of the batch being produced. The goal is to remove moisture from the chips without overcooking them, achieving the perfect crunch while preserving the uniform shape. The frying process takes only a matter of seconds, but within that short time, several crucial chemical reactions occur. The high heat causes the remaining water content inside the dough to rapidly evaporate, creating tiny air pockets that give Pringles their distinctive lightness. At the same time, the starches and sugars in the dough undergo the Maillard reaction, a chemical process that causes browning and enhances the chip's flavor by developing rich, slightly nutty, and toasted notes. Because the chips are fried in a controlled environment while sitting inside their molds, they do not curl or warp the way traditional potato chips do. Instead, they maintain their signature hyperbolic paraboloid shape, which is key to their ability to be stacked efficiently without breaking. To ensure even cooking, the oil circulates through the fryer using a sophisticated system that maintains uniform heat distribution, preventing any chip from becoming overcooked or undercooked. Once the chips have been fried to perfection, they must be quickly removed from the hot oil to prevent excessive absorption of fat, which could compromise their texture and make them overly greasy. The chips exit the fryer onto a draining conveyor, where excess oil is gently shaken off. A series of air jets then blow away any remaining oil droplets, ensuring that each chip has the right balance of crispness without being overly oily. The amount of oil that remains in the final product is carefully monitored, as even a small deviation in fat content could alter the texture and mouthfeel of the chips. After the excess oil is removed, the chips continue along the conveyor system into a specialized drying chamber. This drying stage serves a dual purpose. It helps eliminate any remaining moisture to extend the shelf life of the chips and ensures that they retain their crisp texture. If any residual moisture remains, it could lead to sogginess or even microbial growth, which would compromise the quality of the product. The drying chamber operates using a controlled flow of warm air, which gently removes any lingering humidity without exposing the chips to excessive heat. This is a crucial step because over-drying could make the chips too brittle, leading to breakage before they even reach the packaging stage. The process must strike a balance between removing moisture while preserving the ideal crunch. Now that the chips have been properly fried and dried, they still lack one essential component: flavor. While the dough contains some base seasonings, such as salt, the majority of Pringles' signature flavors are added after cooking. At this point, the chips are still relatively plain, resembling lightly salted potato crisps. To give them their final taste, they must go through the seasoning process. The chips enter a large rotating drum, which is a key part of the flavoring system. This drum functions much like a giant tumbler, gently tossing the chips to ensure that each one is evenly coated with seasoning. However, before the seasoning can be applied, the chips must be lightly misted with a fine spray of oil. This thin coating of oil acts as an adhesive, allowing the seasoning to stick uniformly to each chip without clumping. Once the oil mist has been applied, the chips move further into the drum, where a precise amount of seasoning powder is dispensed. This powder is a proprietary blend of dehydrated spices, artificial and natural flavors, and other ingredients that create the distinct taste of each Pringles variety. Whether it's the classic original, sour cream and onion, barbecue, or any of the many other flavors available around the world, each seasoning mix is carefully crafted to deliver a consistent and recognizable taste. The rotation of the drum ensures that the seasoning is distributed evenly across all chips, preventing any one chip from receiving too much or too little flavor. This is crucial because even slight inconsistencies in seasoning distribution can affect the overall eating experience. Too much seasoning on one chip could make it overpowering, while too little could make it bland. The factory's precision-engineered system ensures that every chip in a can has the same delicious taste. To confirm that the seasoning has been applied correctly, automated sensors monitor the amount of seasoning powder dispensed and the overall coating level. These sensors use advanced optical and weight measurement technologies to detect any irregularities in the seasoning process. If an issue is detected, such as an uneven application or a deviation from the standard amount of seasoning, the system can automatically adjust to correct the problem in real time. Now fully seasoned, the chips continue their journey toward the final stages of production. At this point, they must be carefully handled to prevent breakage before they are packaged. Despite their sturdy design, Pringles are still delicate enough to crack if handled too roughly, so the conveyor system is designed to gently transport them through the factory. Before reaching the packaging area, the chips pass through another quality control checkpoint. High-speed cameras and sensors inspect each chip to ensure that they meet the brand's strict standards. Any chips that are overly browned, misshapen, or broken are automatically removed from the line. These rejected chips do not go to waste. They are often ground down and repurposed as part of the raw ingredient mixture for new batches, minimizing food waste in the production process. Now, with their perfect shape, crisp texture, and flavorful coating, the chips are ready for packaging. However, the packaging process itself is an essential part of what makes Pringles so unique. Unlike traditional potato chips, which are packed into bags that allow for some degree of breakage, Pringles are carefully stacked inside rigid cylindrical cans. This design ensures that they remain intact from the moment they leave the factory to the time they are opened by consumers. As the chips approach the packaging area, specialized machines align them into precise stacks. These machines use gentle vibrations and suction mechanisms to ensure that each stack is perfectly arranged before being inserted into the canisters. The stacking process is incredibly precise. Any misalignment could cause the chips to break during transportation. At this point, the Pringles are nearly ready to be sealed and sent out for distribution, but there are still a few final steps left to complete before they can reach store shelves. The packaging must ensure freshness, provide product protection, and meet branding and labeling requirements. In the next stage, the stacked chips will be inserted into cans, sealed for freshness, and prepared for shipment. With the freshly seasoned chips perfectly stacked and aligned, the Pringles are now ready for the crucial packaging stage. This process is just as important as the manufacturing and cooking steps, as it ensures that the chips remain intact and fresh until they reach consumers. Unlike traditional potato chips, which are packed loosely in bags that allow for some level of breakage, Pringles are carefully placed into rigid cylindrical cans, a signature feature that sets them apart from other snack foods. The packaging process begins with the automatic loading of the Pringles stacks into their respective canisters. These canisters, made from a combination of cardboard and aluminum lining, are designed to provide structural support, protecting the delicate chips from breaking during transport. The cans arrive at the packaging station in a flattened state and are quickly formed into their cylindrical shape by specialized machinery. The inner lining of the cans is coated with a food-safe aluminum layer, which helps to preserve freshness by preventing exposure to moisture and air. Once the cans are fully formed, they are transported to the filling station, where the Pringles stacks are precisely inserted into them. This process requires extreme precision, as any misalignment could cause the chips to shift or break. A combination of gentle vibrations and suction mechanisms ensures that the stacks remain stable as they are guided into the canisters. If even a single chip in the stack is out of place, the entire batch may be rejected to maintain quality standards. As the filled cans move along the conveyor, they reach the sealing station, where a thin foil seal is applied to the top of each canister. This foil seal serves multiple purposes. It locks in freshness, prevents air from entering, and ensures that the chips remain crisp for an extended period. The application of the seal is a highly controlled process that uses a combination of heat and pressure to create an airtight bond between the foil and the can's rim. Automated sensors continuously monitor the sealing process, detecting any imperfections or leaks. If a faulty seal is identified, the can is removed from the production line and either reprocessed or discarded. After the foil seal is in place, a plastic lid is applied to the top of the can. This lid serves as a secondary protective barrier and allows consumers to reseal the container after opening. The lids are typically made from lightweight but durable plastic that ensures a secure fit while remaining easy to remove. Before being placed onto the cans, the lids are inspected for defects, such as warping or cracks, which could compromise the product's freshness. With the Pringles cans now fully assembled and sealed, they move toward the labeling and branding station. Here, pre-printed labels featuring the Pringles logo, flavor designation, and nutritional information are carefully wrapped around each canister. These labels are made from high-quality materials that are resistant to moisture and tearing, ensuring that they remain intact throughout the product's journey from the factory to store shelves. A combination of heat and adhesive is used to secure the labels in place, ensuring a smooth, wrinkle-free application. Once labeled, the finished cans undergo another round of quality control checks. Automated cameras and sensors scan each can to verify that the labels are correctly applied and free of defects. Any cans with misaligned or damaged labels are removed from the line and either relabeled or discarded. Additionally, random samples from each batch are taken for more detailed inspections, where factory workers check for overall product integrity, including stack alignment, sealing effectiveness, and crispness. After passing the final quality control checks, the Pringles cans are grouped together for bulk packaging. This step involves placing multiple cans into larger cardboard cartons or shrink-wrapped bundles, which make transportation and stocking more efficient. The bulk packaging process is automated, with robotic arms carefully arranging the cans into pre-formed boxes or wrapping them in durable plastic film. The goal is to maximize space efficiency while ensuring that the cans are securely held in place to prevent movement during shipping. Once the bulk packaging is complete, the cartons are sealed and labeled with batch numbers, expiration dates, and tracking information. These labels allow for easy inventory management and ensure that products can be traced back to their specific production batch if necessary. The cartons are then stacked onto pallets, which are loaded onto trucks for distribution to retailers, supermarkets, and convenience stores around the world. Before being shipped out, the finished products undergo a final inspection to verify that the correct quantities and flavors have been packed for each order. Logistics teams coordinate with distribution centers to determine the most efficient shipping routes, ensuring that Pringles reach their destinations as quickly and cost-effectively as possible. Since Pringles are a globally recognized brand, this distribution network spans multiple countries, requiring careful coordination between factories, warehouses, and retailers. Throughout this entire process, Pringles manufacturers adhere to strict hygiene and safety regulations to ensure product quality and consumer safety. Factory workers follow rigorous sanitation protocols, wearing protective gear such as gloves, hairnets, and face masks to prevent contamination. the production facilities are regularly inspected by quality assurance teams and food safety organizations to ensure compliance with industry standards. In addition to maintaining high production standards, Pringles manufacturers are constantly exploring ways to improve sustainability and reduce waste. The company has implemented initiatives to minimize environmental impact, such as optimizing energy usage in production plants, recycling excess packaging materials, and reducing food waste by repurposing rejected chips and excess dough. In some regions, Pringles packaging has been redesigned to use more eco-friendly materials, with ongoing efforts to further enhance the sustainability of the product. While the cans of Pringles are now ready to be shipped to stores, the journey does not end there. Once they arrive at retail locations, they must be carefully stocked to ensure they remain in pristine condition for customers. Store employees follow specific stocking guidelines to prevent the cans from being crushed or stacked improperly. The cylindrical shape of the canisters allows them to be displayed neatly on shelves, creating an organized and visually appealing presentation. For consumers, the convenience of Pringles packaging is one of its most attractive features. The resealable lid allows snackers to enjoy the chips at their own pace while keeping them fresh between servings. Unlike traditional chip bags that often trap excess air and lead to crushed chips, the rigid canister provides a level of protection that helps maintain the product's quality. The success of Pringles is not only due to the meticulous manufacturing process, but also to the brand's ability to continually innovate. Over the years, new flavors and limited edition varieties have been introduced to cater to different tastes and cultural preferences. Research and development teams work to create unique seasoning blends and textures that keep consumers engaged with the brand. In some cases, local flavors are developed exclusively for specific markets, adding an element of regional customization. With the fully sealed and labeled Pringles cans ready for shipment, the final step in the manufacturing process involves distribution and logistics. Once the pallets of Pringles leave the factory, they are sent to distribution centers where they are sorted based on destination. From here, they are shipped to retail locations around the world, including supermarkets, convenience stores, vending machines, and online retailers. One of the key advantages of Pringles' packaging is its durability. Unlike traditional potato chips that are shipped in large bags, prone to air compression and breakage, Pringles' rigid canisters allow for efficient stacking and transport without excessive damage. This means fewer chips are wasted due to breakage during shipping, making the product more cost-effective and reducing food waste. At the retail level, Pringles cans are often displayed in neat, vertical arrangements on shelves, taking advantage of their cylindrical shape. This design not only protects the chips, but also maximizes shelf space compared to bulky chip bags. Supermarkets and convenience stores follow specific stocking guidelines to ensure that Pringles cans remain undamaged and easily accessible to customers. Once purchased, consumers benefit from the resealable can, which keeps the chips fresh longer than traditional bags. Unlike conventional chip bags that often allow air to seep in after opening, leading to stale chips, Pringles' airtight design helps maintain their signature crunch over multiple servings. This has been a significant selling point for the brand and one of the reasons for its continued popularity. Beyond the production process, the Pringles brand continues to evolve. The company regularly develops new flavors, incorporating regional tastes and limited edition releases to cater to different markets. Flavors such as wasabi, pizza, and even dessert-inspired varieties have been introduced over the years, keeping the brand relevant and exciting for consumers. In recent years, sustainability has become a growing concern, leading to efforts to improve the recyclability of Pringles packaging. This journey starts with sourcing high-quality peanuts, primarily from regions renowned for their optimal growing conditions, such as Georgia and Texas. These areas provide the ideal climate and soil composition, resulting in peanuts with the desired size, flavor, and oil content essential for the signature Reese's taste. Upon arrival at the manufacturing facility, the peanuts are subjected to a rigorous inspection process. Advanced optical sorting machines, equipped with high-resolution cameras and sensors, meticulously scan each peanut, identifying and removing any that are discolored, misshapen, or contaminated with foreign materials. This ensures that only the finest peanuts proceed to the next stage, maintaining the high-quality standards synonymous with Reese's products. Following sorting, the peanuts undergo a thorough cleaning process. They are funneled through a series of air classifiers and vibrating screens that effectively remove dirt, stones, and other debris. Some facilities may also employ water baths or steam cleaning methods to ensure an even higher level of cleanliness. This step is crucial, as any residual impurities could adversely affect the flavor and safety of the final product. The next phase involves roasting the cleaned peanuts to develop their rich, nutty flavor and achieve the desired texture. Industrial roasters, such as continuous belt roasters or rotary drum roasters, are employed to ensure even roasting. The peanuts are exposed to temperatures ranging from 320 degrees Fahrenheit to 350 degrees Fahrenheit for a specific duration, typically between 30 to 60 minutes. The exact time and temperature are carefully controlled and adjusted based on factors like peanut variety and moisture content to achieve the optimal roast profile. During roasting, the Maillard reaction, a chemical interaction between amino acids and reducing sugars, occurs, contributing to the development of complex flavor compounds and the characteristic golden brown color of the peanuts. Continuous monitoring of temperature and airflow within the roasters ensures uniform roasting and prevents over or undercooking, which could compromise the flavor and quality of the peanut butter filling. Once roasting is complete, the peanuts are rapidly cooled to halt the cooking process and preserve their flavor profile. This is typically achieved by passing the hot peanuts through cooling conveyors equipped with powerful fans that circulate ambient air. Rapid cooling prevents the peanuts from continuing to cook from residual heat, which could lead to undesirable flavor changes or textural issues. After cooling, the peanuts are transferred to blanching machines, where their skins are removed. Blanching involves exposing the peanuts to steam or hot air to loosen the skins, followed by mechanical rubbing or abrasion to peel them away. This step is essential, as peanut skins can impart a bitter taste and affect the smoothness of the peanut butter. The blanched peanuts are then inspected once more to ensure all skins and any remaining impurities have been effectively removed. The blanched peanuts are now ready for grinding, a critical step in transforming them into the creamy peanut butter that fills each Reese's cup. The peanuts are fed into industrial grinders, which consist of a series of grinding plates or mills that progressively reduce the peanut particles to the desired consistency. The initial grinding stage breaks the peanuts into coarse pieces, while subsequent stages further refine the texture, resulting in a smooth, creamy peanut butter. Throughout the grinding process, the peanut's natural oils are released, contributing to the creamy consistency of the peanut butter. To achieve the perfect texture and prevent oil separation, stabilizers such as hydrogenated vegetable oils may be added. These stabilizers help maintain the emulsion of peanut solids and oils, ensuring the peanut butter remains smooth and spreadable over time. Temperature control during grinding is paramount. Excessive heat generated by friction can alter the flavor and consistency of the peanut butter. To mitigate this, cooling systems are integrated into the grinding equipment, maintaining the peanut butter at an optimal temperature and preserving its quality. Once the peanut butter reaches the desired consistency, it is transferred to stainless steel storage tanks equipped with agitation systems. These systems keep the peanut butter uniformly mixed, preventing the settling of solids and ensuring consistency across batches. The storage tanks are part of a closed system that protects the peanut butter from exposure to air and potential contaminants, preserving its freshness and flavor until it is needed for the next stage of production. Now, it's time to delve into the preparation of the chocolate coating that envelops the peanut butter filling, giving Reese's peanut butter cups their iconic taste and texture. The chocolate used is a carefully formulated blend designed to complement the peanut butter's flavor while providing a smooth and satisfying mouthfeel. The process begins with the selection of premium cocoa beans, sourced from regions known for their high-quality cocoa production, such as West Africa and South America. These beans are fermented and dried at their origin to develop the foundational flavor characteristics essential for quality chocolate. Upon arrival at the manufacturing facility, the cocoa beans undergo roasting, a process that further develops their flavor and reduces moisture content. Industrial-scale roasters, similar to those used for peanuts, are employed to ensure even roasting. The beans are roasted at temperatures between 250 degrees Fahrenheit to 320 degrees Fahrenheit for durations ranging from 30 to 60 minutes, depending on the desired flavor profile. Continuous monitoring ensures consistency and prevents over-roasting, which could impart bitter notes to the chocolate. After roasting, the cocoa beans are cooled and subjected to winnowing, a process that removes the outer shells, leaving behind the valuable cocoa nibs. These nibs are then ground into cocoa mass, also known as cocoa liquor, which serves as the base for all chocolate products. The grinding process generates heat, causing the cocoa butter within the nibs to melt and form a liquid mass. To create milk chocolate, the variety used in Reese's peanut butter cups, the cocoa mass is combined with specific proportions of sugar, milk solids, and additional cocoa butter. This mixture undergoes refining, where it is passed through a series of rollers to reduce particle size, resulting in a smoother texture. Achieving the optimal particle size is crucial, as it influences the mouthfeel and overall quality of the chocolate. Following refining, the chocolate mixture undergoes conching, a process involving continuous mixing and aeration at controlled temperatures. Conching serves multiple purposes. It further smooths the texture, develops flavor by promoting the evaporation of undesirable volatile compounds, and ensures a homogeneous blend of ingredients. The duration and temperature of conching are carefully controlled, with longer conching times typically resulting in superior flavor development. Once conching is complete, the chocolate is tempered to stabilize its crystalline structure. Tempering involves carefully cooling and reheating the chocolate to specific temperatures, encouraging the formation of stable cocoa butter crystals. Proper tempering ensures that the chocolate sets with a glossy finish, has a satisfying snap, and resists blooming, a condition where fat or sugar crystals rise to the surface, creating a dull or streaked appearance. The tempered chocolate is maintained at a precise temperature in holding tanks, ready for the enrobing process. These tanks are equipped with gentle agitation systems to keep the chocolate uniformly mixed and at the correct viscosity for coating the peanut butter filling. But up next is the integration of the peanut butter filling and the chocolate coating, a process that demands precision and synchronization to achieve the perfect balance between the two components. Specialized machinery is employed to deposit measured amounts of peanut butter onto a base layer of chocolate, ensuring consistency in size and weight for each cup. The process begins with the formation of the chocolate shell. Molds, typically made of polycarbonate or stainless steel, are filled with a specific amount of tempered milk chocolate, dispensed through precision-controlled nozzles. These molds then pass through a vibration station which ensures the chocolate evenly coats the bottom and sides of the mold cavity. This vibration also helps eliminate any air bubbles that could compromise the integrity or appearance of the finished product. The amount of chocolate deposited and the intensity of vibration are both tightly regulated, ensuring uniformity across thousands of cups produced per hour. Once the molds are coated, they are inverted and lightly spun in a controlled environment. This inversion allows excess chocolate to drain off while still leaving a consistent layer adhered to the inner surfaces of each mold. This stage is crucial. Too much chocolate can overwhelm the peanut butter filling, and too little can lead to structural failure of the cup during demolding or packaging. The molds then proceed through a cooling tunnel, typically kept at temperatures between 45 degrees Fahrenheit and 55 degrees Fahrenheit. The cooling phase ensures that the chocolate shell partially sets to the correct hardness before it receives the peanut butter filling. As the molded chocolate shells emerge from the cooling tunnel, they are transported to the filling station. Here, a high-speed depositor arm, equipped with precision temperature and viscosity control, deposits the peanut butter filling into each partially set chocolate cup. The filling temperature is typically maintained between 85 degrees Fahrenheit and 95 degrees Fahrenheit, warm enough to flow smoothly, but cool enough not to melt or deform the chocolate shell. The depositor is calibrated to deliver an exact volume of filling per cup, down to a fraction of a milliliter. This exactness is essential for product consistency and for ensuring that the peanut butter doesn't spill over the edges when the top chocolate layer is added. The formulation of the peanut butter filling used in Reese's is slightly different from traditional peanut butter. It is intentionally thicker and drier in consistency, achieved by controlling the moisture content and fat levels during the grinding and mixing process. This formulation helps the filling maintain its shape during deposition and ensures it doesn't mix into or bleed through the surrounding chocolate. The peanut butter also contains a precise blend of sugar, salt, and stabilizers, all tailored to produce the sweet, slightly salty, and crumbly texture unique to Reese's cups. After the filling is deposited, the molds move on to receive the final chocolate layer. This top layer of tempered chocolate is again dispensed with precision, covering the peanut butter entirely and sealing the cup. The exact thickness of this layer is calibrated to ensure a perfect balance between the two flavors and to provide structural integrity once the product is unmolded. If the chocolate top is too thin, it risks cracking during cooling and handling. Too thick, and it throws off the flavor harmony. The fully assembled peanut butter cups then enter a second cooling tunnel. This tunnel is longer and colder than the first, typically operating between 35 degrees Fahrenheit and 45 degrees Fahrenheit. Here, the final chocolate layer sets completely, bonding with the underlying components and solidifying the cup into its final form. Conveyor belts inside the tunnel are carefully speed regulated so that the cups spend the exact amount of time needed to fully crystallize the cocoa butter without overcooling, which could lead to bloom or textural issues. As the cooled and fully set cups exit the tunnel, they are transported to the demolding station. This is a delicate and crucial phase where the now solid chocolate cups must be removed from their molds without cracking, chipping, or leaving any residue behind. Modern factories use pneumatic or mechanical release systems that gently flex the molds while applying a quick burst of air from underneath each cavity. This loosens the cups and lifts them onto a secondary conveyor without physical contact from human hands, preserving hygiene and preventing product damage. Now it's time to go into the inspection and quality control stage, a multi-layered process where each Reese's peanut butter cup is evaluated for conformity, appearance, and safety. As the demolded cups travel along the inspection conveyor, they pass through high-resolution vision systems equipped with artificial intelligence software that scans for imperfections. This includes checking for chips in the chocolate, uneven layers, off-center fillings, or improperly formed edges. Cups that do not meet the strict visual criteria are automatically rejected by air jets that direct them off the main line and into collection bins for disposal or reprocessing, depending on company policy and food safety regulations. In addition to visual checks, random samples are pulled at regular intervals for more in-depth testing. These samples are weighed to ensure they meet exacting product specifications. Other tests may include breaking the cup in half to examine the internal peanut butter to chocolate ratio, or using texture analyzers that measure the product's resistance to pressure, an indicator of proper tempering and filling density. Chemical testing is also conducted regularly to verify the correct balance of sugar, moisture, fat, and salt in the filling. These tests are often performed in on-site quality control laboratories, where technicians run batch samples through a range of analytical equipment, such as moisture analyzers, gas chromatographs, and spectrophotometers. If any irregularities are found, production is paused, and corrective measures are implemented. This could mean recalibrating a depositor nozzle, adjusting roasting temperatures for peanuts, or even reviewing the supply chain for ingredient inconsistencies. But up next is the packaging stage, which begins with the alignment of the peanut butter cups into lanes that feed into high-speed wrapping machines. These machines are capable of wrapping hundreds of cups per minute, and they must do so without damaging the fragile chocolate shell. The wrapper material is typically a laminated foil paper composite, selected for its barrier properties against oxygen, moisture, and light, all of which can degrade product quality over time. Each wrapper is printed with the Reese's branding, product information, batch codes, and expiration dates using thermal or inkjet printers. As the cups enter the wrapping station, they are placed onto rotating belts that synchronize with the wrapper feed. A roll of pre-printed wrapping film is continuously pulled into position, cut to size by high-speed blades, and sealed around each cup using heated crimpers. The sealing temperature and pressure must be carefully controlled to ensure an airtight seal without melting the chocolate inside. Once wrapped, the cups are grouped for secondary packaging. They may be placed in cardboard sleeves, plastic trays, or directly into multi-unit bags, depending on the product configuration. These groups are then placed into larger cartons for shipping. Before sealing, a final barcode scanner checks each item to confirm it matches the correct SKU and batch. Any errors trigger an automatic halt in the packing line to prevent cross-contamination between different product types. Every carton is weighed and scanned one final time before being sealed, labeled, and moved to the warehouse staging area. From here, pallets of Reese's peanut butter cups are logged into an inventory system and scheduled for distribution to retail locations across the country. Every step from peanut to pallet is tracked with traceability data, ensuring full accountability throughout the production cycle. Now it's time to go into the warehousing and distribution phase of Reese's peanut butter cup production, where the finished products transition from tightly controlled factory environments to large-scale logistics operations. Once the individually wrapped and secondary packaged cups are assembled into master cartons, these cartons are loaded onto pallets. Each pallet holds a predefined number of cartons, strategically arranged to optimize space while maintaining product integrity during transport. Automated palletizers equipped with robotic arms or gantry systems handle this process with precision, stacking cartons with minimal human intervention to ensure efficiency and reduce labor costs. Once a pallet is completed, it's secured using high tensile stretch wrap, often applied via automated rotary arm or turntable wrapping machines. This stretch film not only stabilizes the load, but also provides a moisture and dust barrier, safeguarding the products during storage and shipping. Pallets are then labeled with barcoded shipping tags that include vital information such as product codes, batch numbers, production dates, and destination data. These barcodes are integrated into the factory's centralized inventory management system, allowing for real-time tracking and traceability from the moment a product leaves the production floor. The wrapped and labeled pallets are then moved to climate-controlled storage areas within the facility's warehouse. These storage zones are maintained at stable temperatures, typically between 55 degrees Fahrenheit and 70 degrees Fahrenheit, to ensure the chocolate remains in perfect condition. Extreme heat can cause melting or blooming, while excessive cold may alter texture or create condensation that can compromise the packaging seal. Environmental sensors continuously monitor these storage areas, and any deviation outside preset tolerances triggers alerts for immediate corrective action. Warehouse operations are managed by advanced warehouse management systems, which direct the flow of goods through automated guided vehicles or forklifts, guiding them to the optimal racking locations based on FIFO principles. This ensures older inventory is shipped before newer batches, reducing the risk of aging stock reaching consumers. Some high-output facilities even use fully automated storage and retrieval systems, where robotic cranes handle all inbound and outbound movement of pallets without human inputs. As orders come in from distribution centers, retail chains, or e-commerce platforms, the WMS generates pick lists, directing operators or picking robots to assemble the correct products for shipment. During the picking process, each item's barcode is scanned again to confirm accuracy. Pallets are then loaded onto temperature-controlled trucks or shipping containers, with the logistics team carefully planning routes and loading sequences to match delivery schedules. The transportation phase is critical in preserving product quality. Trucks used to transport Reese's peanut butter cups are often equipped with refrigeration units to maintain stable conditions, especially during warmer months or in hot climates. Real-time GPS tracking and telematics systems allow logistics managers to monitor vehicle locations and environmental conditions inside the trailers, ensuring any issues can be addressed proactively. Once the Reese's cups arrive at regional distribution centers, they're cross-docked or stored temporarily before being sent to individual retail locations. Cross-docking minimizes storage time by immediately transferring incoming goods to outgoing trucks, improving freshness and reducing inventory holding costs. At the retail level, automated shelf replenishment systems and electronic point-of-sale data further refine logistics by signaling when to restock based on actual consumer purchases, closing the loop between factory and final sale. Now it's time to explore the role of factory automation and digital systems that underpin every phase of Reese's peanut butter cup production. From peanut sorting to final product distribution, automation enhances consistency, efficiency, and food safety across the board. At the front end of the process, smart sensors and machine vision systems oversee raw ingredient inspection. These tools can detect flaws invisible to the human eye, such as slight discoloration, mold, or the presence of foreign matter, ensuring that only the highest quality peanuts and cocoa beans enter the process. Programmable logic controllers orchestrate the flow of operations on the production line. These industrial computers are connected to every piece of equipment, from roasters and grinders to depositors and cooling tunnels, and execute real-time instructions based on input data. For example, if a change in peanut moisture content is detected by inline sensors, the PLC can automatically adjust roasting time or temperature to compensate, maintaining flavor consistency. Supervisory control and data acquisition systems provide plant operators with a bird's eye view of the entire production environment. With these interfaces, managers can monitor batch progress, verify line speeds, track downtime, and receive alerts if any machinery falls out of spec. Every action taken by machines is logged for traceability, which is particularly important for food safety compliance and auditing purposes. Data collected from SCADA systems can also be analyzed for continuous improvement, helping to identify bottlenecks, optimize throughput, and reduce energy consumption. Robotics play a crucial role in packaging and material handling. Articulated robotic arms, equipped with suction grippers or vision-guided end effectors, perform tasks such as picking and placing cups into trays, applying labels, or stacking cartons. These robots can work around the clock without fatigue, dramatically improving productivity while maintaining precision and reducing injury risk for human workers. Factory hygiene and sanitation are also managed with the help of automation. Clean-in-place systems are installed throughout the facility to automatically flush and sanitize processing lines between batches. These systems circulate heated cleaning solutions through tanks, pipes, and machinery to remove peanut residue and chocolate buildup, all without disassembling equipment. Sensors measure cleaning effectiveness in real time, ensuring that microbial standards are met and that no allergenic cross-contact occurs between production cycles. But up next is the innovation behind product design and the proprietary formulation that gives Reese's Peanut Butter Cups their legendary status. While the general public recognizes the product for its flavor, texture, and iconic shape, much of the success lies in the precise engineering of ingredients and design. The ratio of peanut butter to chocolate has been refined over decades of experimentation, resulting in a balance that optimizes sweetness, saltiness, creaminess, and firmness. Hershey's R&D teams use texture analysis, sensory panels, and predictive modeling to test thousands of variations in ingredient proportions before locking in a final formula. Ingredient consistency is paramount. For instance, the type of sugar used in the peanut butter filling is selected not just for sweetness, but for its ability to control water activity and crystallization during storage. The salt content is finely tuned to enhance the peanut flavor without becoming overpowering, while milk powder used in the chocolate is selected for both its taste and its emulsifying properties. Even minor fluctuations in these ingredients can affect the final mouthfeel and flavor, which is why tight supplier controls and internal batch testing are enforced. The cup shape and wrapper design are also engineered with precision. The signature fluted edge of each Reese's cup isn't just a visual cue. It aids in demolding and adds structural strength. The cups are formed using molds with concentric grooves that create this pattern as chocolate is spun or vibrated up the walls. The wrapper is designed to peel off easily without sticking to the chocolate, which requires selecting specific coatings and materials that interact correctly with cocoa butter at varying humidity levels. In recent years, innovation has also extended to creating new product lines, miniatures, thins, big cups, and seasonal shapes. Each variant requires its own custom set of tooling, depositor calibrations, and process flow adjustments to accommodate differences in fill volume, chocolate thickness, and packaging format. These product changes often involve months of pilot testing on R&D lines before being scaled to full production. Engineers simulate the behavior of chocolate and peanut butter under different conditions using computational fluid dynamics models, ensuring that no matter the shape or size, the Reese's experience remains consistent. Every year, the production line adapts to create special seasonal versions of Reese's Peanut Butter Cups, which introduces another layer of complexity to the manufacturing process. For Halloween, pumpkin-shaped cups are crafted, while Christmas brings tree-shaped varieties and Easter features egg-shaped versions, all of which require entirely different molding systems. Instead of the standard fluted cup molds used year-round, these limited editions use custom-engineered molds with unique contours that must still ensure even chocolate distribution, stable cooling, and a clean release during demolding. These seasonal shapes often necessitate recalibrating the chocolate depositor systems and modifying the cooling tunnel timings, since broader or thicker designs may set at different rates than standard cups. Flour is the primary component, usually made from wheat, and it is carefully milled to achieve the right texture and protein content for cake production. Sugar is another crucial ingredient, providing sweetness and structure to the cake batter. Granulated sugar, powdered sugar, and sometimes liquid glucose are used depending on the specific type of cake being manufactured. Eggs, either fresh or in liquid or powdered form, contribute to the structure and moisture of the cake. Dairy ingredients such as butter, milk, and cream enhance the flavor and texture. Vegetable oils, often used as a substitute for butter in large-scale production, ensure a longer shelf life and a softer crumb. Leavening agents such as baking powder or baking soda are essential to create the airy texture that defines a good cake. Flavoring agents including vanilla extract, cocoa powder, fruit purees, and artificial flavors are precisely measured and incorporated to achieve consistent taste profiles. Before production begins, the factory undergoes rigorous sanitation procedures to ensure a clean environment. Production lines, mixers, conveyors, and baking equipment are all sterilized to prevent contamination. The ingredients are stored in temperature-controlled silos or containers, with automated systems regulating their dispensation. Large-scale cake production begins with precise ingredient measurement. Factories utilize automated weighing systems that ensure every batch maintains the correct proportions. Dry ingredients like flour, sugar, and leavening agents are sifted and aerated to remove clumps before entering the mixing phase. Liquid ingredients such as eggs, milk, and oils are stored in large tanks and piped directly into the mixing units. Mixing is a critical step in cake production, requiring advanced industrial mixers that can handle large volumes while maintaining consistency. The process varies depending on the type of cake being produced. Sponge cakes require aeration to create a light texture, while denser cakes need thorough mixing to ensure a uniform crumb. Continuous batter mixing systems operate at high speeds, gradually incorporating the ingredients in precise sequences. Some factories use planetary mixers, which rotate on multiple axes to create an even distribution of ingredients. Ribbon blenders or high shear mixers may also be used to emulsify fat-based batters. Mixing times and speeds are carefully programmed to avoid overmixing, which can result in tough cakes. Once the batter reaches the desired consistency, it is transferred through a network of pipes or conveyor belts to the depositing machines. These machines portion the batter into molds, trays, or baking pans, ensuring uniformity in weight and shape. Modern cake factories employ volumetric or piston-based depositors that release precise amounts of batter with each cycle. Some machines are equipped with multiple nozzles to fill several trays simultaneously, increasing efficiency. At this stage, additional ingredients such as fruit pieces, nuts, or chocolate chips may be incorporated, either mixed into the batter or sprinkled on top before baking. The filled molds or trays move along a conveyor system into industrial ovens. The baking process is meticulously controlled to achieve the desired texture and color. Tunnel ovens, rack ovens, and convection ovens are commonly used in large-scale cake production. Tunnel ovens, which feature continuous conveyor belts that move cakes through different temperature zones, ensure even baking. The temperature and humidity levels within the ovens are carefully regulated to promote consistent rising and moisture retention. During baking, leavening agents react with heat to create gas bubbles, causing the batter to expand. The Maillard reaction, a chemical process between amino acids and sugars, develops the golden brown crust and enhances flavor. After baking, the cakes must be cooled to prevent condensation and sogginess. Cooling tunnels equipped with controlled airflow rapidly bring down the temperature while preventing excessive moisture loss. The cooling process is crucial because cakes that are too warm can compromise the integrity of icing or packaging. Factories often employ spiral cooling conveyors that maximize space efficiency while allowing cakes to cool gradually. Some facilities use blast coolers that rapidly reduce temperatures without affecting texture. Once sufficiently cooled, cakes may be removed from their molds using automated depanning systems. These machines use gentle vibrations, air pressure, or mechanical arms to lift cakes without damaging their shape. Before proceeding to decoration, quality control checks are performed. Cakes are inspected for uniformity in size, shape, and color. Advanced vision inspection systems use cameras and sensors to detect defects such as uneven surfaces or air pockets. Weight sensors ensure each cake meets the required specifications. Any cakes that do not pass quality checks are either reworked or discarded. Some factories employ metal detectors and X-ray scanners to identify foreign objects or contaminants. The decoration process varies depending on the type of cake being produced. For layer cakes, automated slicing machines cut the cakes horizontally to create multiple layers. These layers are then conveyed to filling stations, where robotic arms or extrusion nozzles apply cream, fruit preserves, or ganache. In some cases, conveyor systems transport the cakes through enrobing machines, which coat them in a layer of chocolate or glaze. Icing and frosting are applied using precision nozzles, spatula robots, or rotary icing machines. Buttercream, fondant, or whipped cream is spread evenly across the surface. Some factories use airbrush systems to add gradients of color or decorative effects. For cakes that require intricate designs, programmable robotic arms pipe decorative elements with incredible precision. Sprinkles, chocolate shavings, or edible glitter may be added using automated dispensers. At this stage, cakes intended for retail packaging may be pre-sliced using ultrasonic cutting machines. These machines utilize high-frequency vibrations to create clean, precise cuts without crushing the delicate cake structure. Pre-sliced cakes are often packaged in individual portions for convenience. Cakes intended for long shelf life may undergo additional processes such as modified atmosphere packaging, which removes oxygen from the packaging to slow down spoilage. Packaging is a crucial step in maintaining product freshness and ensuring a visually appealing presentation. Cakes are carefully transferred onto packaging conveyors, where they are placed into plastic trays, paperboard cartons, or clamshell containers. Flow wrapping machines seal individual cakes in airtight film to extend shelf life. For larger cakes, shrink wrapping or rigid plastic domes provide protection during transportation. Labels with product information, barcodes, and expiration dates are applied using automated labeling machines. Before distribution, final quality control checks are performed. Cakes are weighed again to confirm portion accuracy. Some factories conduct random sampling to test for taste, texture, and moisture content. Microbiological testing may be carried out in on-site laboratories to ensure food safety compliance. Cakes are then organized into cartons or crates and palletized for transportation. Temperature-controlled storage areas maintain product freshness before shipment. Depending on distribution requirements, cakes may be transported in refrigerated trucks to prevent spoilage. Large-scale manufacturers distribute cakes to supermarkets, bakeries, and retailers across vast geographical areas. Once the cakes are packed and ready for distribution, they move through a final inspection stage to ensure that packaging integrity is maintained. Automated vision inspection systems scan the packaging for any defects, such as improper sealing, misaligned labels, or damage that could compromise product quality. Any faulty packages are removed from the production line to prevent them from reaching consumers. At this stage, lot numbers and expiration dates are printed onto the packaging using high-speed inkjet printers or laser etching machines, allowing for precise tracking and traceability. This is a critical aspect of food safety regulations, as it enables quick recalls in the unlikely event of contamination or quality issues. Once the cakes have passed all final quality control checks, they are transported to cold storage or distribution centers. Cakes that require refrigeration, such as those with fresh cream or perishable fillings, are stored in temperature-controlled environments to maintain freshness. These storage areas are monitored by advanced refrigeration systems that maintain optimal humidity and temperature levels. Cakes that have been designed for longer shelf life, such as those using modified atmosphere packaging or preservatives, may be stored at ambient temperatures before shipping. Distribution logistics are carefully planned to ensure that cakes reach their destination in perfect condition. Large-scale cake manufacturers work with refrigerated trucking fleets and logistics providers to manage transportation efficiently. Cakes are loaded onto pallets and organized based on their destination, with detailed inventory tracking ensuring that products arrive at the correct locations. In some cases, cakes are shipped directly to supermarkets, bakeries, or food service providers, while others are sent to central warehouses for further distribution. To minimize damage during transit, cakes are packed in sturdy shipping containers designed to absorb vibrations and prevent movement inside the truck. Upon arrival at their final destination, cakes are unpacked and stocked on store shelves or refrigerated display cases. Retailers follow strict storage guidelines to maintain freshness, ensuring that temperature-sensitive cakes are kept in chilled conditions and that all products are rotated based on their expiration dates. Many cakes are sold in pre-packaged formats, while others are displayed in bakery sections where customers can purchase whole cakes or slices. Supermarkets and bakery chains often use just-in-time inventory management systems to minimize waste and ensure a steady supply of fresh cakes. While the majority of factory-made cakes are mass-produced for supermarkets and retail stores, some facilities specialize in producing cakes for commercial bakeries, restaurants, and catering businesses. These cakes are often supplied in bulk, either as frozen cakes that can be thawed and decorated on site, or as partially finished products that can be customized before serving. This flexibility allows bakeries and food service providers to offer fresh cakes without the need for extensive in-house baking operations. The industrial cake making process has evolved significantly over the years, incorporating advanced automation, robotics, and data-driven quality control systems to improve efficiency and consistency. Modern factories utilize artificial intelligence and machine learning to analyze production data, predict maintenance needs, and optimize ingredient usage. Automated production lines can run continuously with minimal human intervention, reducing labor costs and increasing output capacity. One of the most significant innovations in large-scale cake production is the development of high-speed depositing and baking systems. Traditional cake production required separate steps for mixing, portioning, and baking, but modern inline systems integrate these processes seamlessly. For example, continuous mixing systems automatically adjust ingredient ratios based on real-time monitoring, ensuring that each batch maintains the perfect consistency. Depositing machines equipped with servo-driven technology can rapidly change portion sizes, allowing for the production of different cake varieties on the same production line. Baking technology has also advanced, with energy-efficient ovens that use infrared heating and precision airflow systems to achieve uniform baking. These ovens are designed to minimize heat loss, reducing energy consumption while maintaining consistent product quality. Some modern bakeries use hybrid ovens that combine conventional and microwave heating to speed up the baking process without compromising texture. In addition to traditional cakes, many factories produce specialty cakes that cater to specific dietary needs and preferences. Gluten-free cakes, for example, require dedicated production lines to prevent cross-contamination with wheat flour. These cakes use alternative flours, such as rice flour, almond flour, or tapioca starch, along with modified stabilizers to achieve the desired texture. Similarly, vegan cakes are made without eggs or dairy, relying on plant-based substitutes such as flaxseed, aquafaba, and non-dairy milk. Sugar-free and low-carb cakes are also growing in popularity, utilizing sugar alcohols or natural sweeteners like stevia to replace traditional sugar. The rise of personalized and custom cakes has led some factories to develop on-demand printing and decoration technologies. Edible ink printers can create intricate designs, logos, or images directly onto cake surfaces, making them ideal for special occasions or corporate branding. Robotic decorators equipped with artificial intelligence can replicate complex piping patterns, allowing for mass customization with minimal human intervention. Some facilities even offer direct-to-consumer cake ordering services where customers can customize flavors, fillings, and decorations before the cake is produced and shipped. Despite the high level of automation in modern cake production, human oversight remains essential to ensure quality and address any potential issues that arise during manufacturing. Skilled food technologists and quality assurance teams continuously monitor production parameters, conduct taste tests, and refine recipes to maintain consistency. Regular equipment maintenance and cleaning schedules are strictly followed to prevent contamination and ensure compliance with food safety standards. Sustainability is an increasing focus in the cake manufacturing industry, with many companies adopting eco-friendly practices to reduce their environmental impact. Ingredient sourcing has shifted towards sustainable palm oil, fair trade cocoa, and locally sourced dairy to support ethical farming practices. Factories are also investing in waste reduction strategies, such as repurposing cake scraps into secondary products like cake pops, or repackaging unsold cakes into discount bakery items. Some manufacturers have implemented water recycling systems and energy-efficient lighting to further minimize their carbon footprint. Packaging innovation is another area of focus, with a shift toward biodegradable and recyclable materials. Traditional plastic cake containers are being replaced with compostable trays, paper-based wraps, and plant-derived biofilms that maintain freshness while reducing plastic waste. Smart packaging solutions, such as freshness indicating labels and QR codes that provide traceability information, are also being explored to enhance the consumer experience. The demand for factory-made cakes continues to grow globally, driven by changing consumer lifestyles, convenience, and the increasing popularity of ready-to-eat desserts. Emerging markets are seeing a surge in industrial cake production as urbanization and income growth lead to higher demand for packaged bakery products. In response, cake manufacturers are expanding their production capacity, investing in new facilities, and adapting their offerings to regional taste preferences. The future of cake manufacturing is expected to see even greater advancements in automation, customization, and sustainability. 3D food printing technology is being explored as a potential innovation that could revolutionize cake decoration and design. AI-driven recipe development could allow manufacturers to create entirely new flavor profiles based on consumer preferences and sensory data. As consumer awareness of health and nutrition grows, factories may develop functional cakes fortified with protein, fiber, or probiotics to cater to evolving dietary trends. One of the most crucial aspects of large-scale cake manufacturing is maintaining absolute consistency across every batch. Consumers expect the same taste, texture, and appearance every time they purchase a cake from a particular brand, and this requires precise control over every stage of production. Factories employ automated recipe management systems that digitally store exact formulations, ingredient ratios, and process parameters. These systems interface directly with mixing and processing equipment, ensuring that every batch is prepared with the same level of precision. Advanced sensors monitor temperature, humidity, and ingredient dispersion, automatically adjusting machine settings if any deviations are detected. Mixing remains one of the most technologically advanced steps in the industrial cake production process. Continuous mixers, which operate non-stop to produce an unbroken stream of batter, have revolutionized large-scale baking. These machines ensure that ingredients are thoroughly combined without overworking the batter, preserving the delicate structure needed for cakes. In some cases, aeration systems introduce controlled amounts of air into the batter to achieve specific textures. The density and fluffiness of sponge cakes, for instance, depend on the precise incorporation of air during mixing. Factories may also use vacuum mixing technology to to remove excess air bubbles and prevent inconsistencies. Once the batter is perfectly blended, it is transferred through high-speed piping systems to the depositing stations. These machines dispense exact portions of batter into baking molds, trays, or individual paper cups for cupcakes. The speed and precision of depositing machines play a critical role in maintaining efficiency, as even a small miscalculation in portioning can lead to product defects or waste. Some depositors use volumetric control, ensuring each mold receives an identical amount of batter, while others rely on piston-driven mechanisms to regulate flow. Factories that produce multiple cake varieties may use multi-head depositing machines capable of filling different molds simultaneously. At this stage, additional mix-ins or toppings may be incorporated. Fruit pieces, chocolate chips, or nuts are often added either before or after depositing, depending on the desired distribution within the cake. Some factories use automated dispensing units that sprinkle toppings evenly across the surface, while others employ injection systems that insert fillings into the center of the cake batter before baking. These injection methods are commonly used for filled cupcakes or specialty cakes with jam, custard, or chocolate centers. The baking process itself is highly controlled, with industrial ovens engineered to ensure even heat distribution. Tunnel ovens, which operate on a conveyor belt system, are the most commonly used in large-scale cake manufacturing. These ovens feature multiple temperature zones that gradually heat the cakes as they move through the baking chamber. The initial phase of baking involves rapid heat transfer to activate leavening agents and promote expansion. As the cakes progress through the oven, moisture is gradually released, setting the structure while maintaining softness. Humidity control is a critical factor in industrial baking. Cakes that lose too much moisture too quickly may become dry, while excess humidity can lead to underbaking or structural collapse. Factories use steam injection systems within ovens to maintain optimal baking conditions. Convection fans circulate hot air evenly, preventing hot spots and ensuring consistent coloration. Some advanced ovens incorporate infrared or microwave-assisted heating to accelerate baking times without compromising quality. Once the cakes emerge from the ovens, they must be cooled carefully to avoid textural inconsistencies. Cooling conveyors transport cakes through controlled environments where temperature and airflow are meticulously regulated. Spiral cooling systems, which maximize space efficiency by stacking conveyors in a vertical spiral, allow for gradual cooling while optimizing factory floor space. Some manufacturers use rapid cooling tunnels equipped with gentle air currents to quickly stabilize cakes intended for immediate packaging. At this stage, cakes may be trimmed, shaped, or portioned according to product specifications. High-speed ultrasonic slicing machines are used for precision cutting, ensuring that each slice maintains a clean edge without crumbling. For layer cakes, industrial slicers divide cakes horizontally, preparing them for filling and stacking. Cakes that require shaping, such as sheet cakes for pre-cut squares, are passed through automated cutting systems that use rotating blades or water jet technology for perfect uniformity. The decoration process is where cakes truly come to life, transforming from simple baked goods into visually appealing products ready for the market. Large-scale factories utilize a combination of robotic systems, automated icing machines, and human decorators for final touches. Buttercream, fondant, or chocolate coatings are applied using enrobing machines or precision icing nozzles. Rotary icing machines create smooth, consistent layers of frosting, while airbrush systems add gradients of color for a professional finish. For cakes requiring intricate designs, robotic decorators equipped with multi-axis arms can replicate complex piping patterns, flowers, or lettering with remarkable accuracy. These machines are programmed to follow specific designs stored in digital templates, allowing manufacturers to mass-produce cakes with customized elements. Some factories use edible ink printers to apply high-resolution images or logos onto cake surfaces, a popular technique for themed birthday cakes and corporate branding. Toppings and embellishments such as sprinkles, chocolate curls, or fruit slices are applied using automated dispensers. Some cakes may pass through a drizzling station where thin streams of chocolate or caramel are added for decorative effect. Cakes requiring additional layers of decoration, such as fondant appliques or edible figurines, are assembled by skilled workers in specialized decoration zones within the factory. Final quality control checks are conducted before packaging. Cakes are inspected for uniformity in shape, frosting consistency, and overall presentation. Some factories employ X-ray scanners and metal detectors to identify potential contaminants or foreign objects within the cakes. Weight sensors verify that each cake meets precise product specifications, and random sampling is conducted for taste testing and texture analysis. Packaging plays a vital role in preserving cake freshness and ensuring product protection during transportation. Depending on the type of cake, various packaging methods are employed. Flow wrapping machines encase individual cakes in airtight plastic film, extending shelf life by preventing exposure to air and moisture. Larger cakes may be placed in rigid plastic containers or cardboard boxes with clear windows for visual appeal. For frozen or refrigerated cakes, vacuum-sealed packaging is often used to lock in freshness. Modified atmosphere packaging, which replaces oxygen with nitrogen or carbon dioxide, helps prevent mold growth and extends shelf stability. Cakes destined for international markets may undergo additional protective measures, such as temperature-controlled shipping containers or specialized packaging to prevent movement during transit. Once packaged, cakes are palletized and loaded onto distribution trucks. Logistics teams coordinate shipments to ensure that products reach their destinations promptly. Some manufacturers supply cakes directly to retail stores, while others distribute them through central warehouses for regional distribution. Refrigerated transport is essential for cakes with perishable ingredients, while shelf-stable varieties are transported under standard conditions. The journey of a cake from the factory to the consumer's table is a testament to the efficiency and precision of modern food manufacturing. The combination of automation, rigorous quality control, and advanced baking technologies ensures that every cake maintains the same high standard of taste and appearance. As consumer preferences evolve, factories continue to innovate, developing new flavors, healthier alternatives, and environmentally sustainable production methods. As cakes leave the factory and make their way to retail stores, bakeries, and food service providers, a highly efficient distribution network ensures that they arrive in perfect condition. Logistics teams work closely with transportation providers to maintain strict temperature controls for cakes that require refrigeration. Cold chain management is essential for ensuring that cakes with fresh cream, custard, or perishable fillings remain safe and retain their intended texture. Refrigerated trucks are equipped with sensors that monitor temperature and humidity levels throughout the journey, providing real-time data to ensure compliance with food safety regulations. For cakes that are shelf-stable, such as packaged sponge cakes, pound cakes, or snack cakes, transportation is more flexible. These products are typically stacked in cartons and palletized to maximize space efficiency. Distribution centers receive shipments and sort cakes based on their final destinations, whether they are headed to supermarkets, convenience stores, or wholesale suppliers. In some cases, cakes are sent to intermediary facilities where additional labeling, repackaging, or regional customization takes place before reaching store shelves. Retailers follow strict inventory management practices to ensure that cakes are sold within their optimal freshness period. Supermarkets and large bakery chains use electronic tracking systems that monitor stock levels and automatically reorder cakes as needed. Cakes with shorter shelf lives are often placed in refrigerated bakery sections, while long-lasting snack cakes are displayed in standard grocery aisles. In many cases, cakes are rotated based on expiration dates to minimize waste, with older stock sold first through strategic shelving placement. For specialty cakes that require customization, such as birthday cakes or event cakes, factories often provide pre-baked cake bases that can be decorated in-store. Retail bakeries receive plain sponge layers, ready-made buttercream, and pre-mixed fillings that allow decorators to assemble and personalize cakes according to customer requests. This hybrid approach combines the efficiency of factory baking with the creative flexibility of in-store decoration. Some supermarket bakeries even utilize edible printing technology to create personalized cake designs on demand, using high-resolution printers that apply edible ink onto sheets of fondant or rice paper. The demand for factory-produced cakes continues to grow as consumers seek convenient, high-quality desserts for various occasions. Large-scale cake manufacturers constantly innovate to meet changing market preferences, introducing new flavors, textures, and dietary options. Seasonal cakes, such as holiday-themed cakes or limited edition flavors, are planned months in advance, with factories adjusting their production schedules to accommodate demand spikes. These cakes often feature special packaging, festive decorations, or unique flavor combinations that align with holiday traditions and cultural celebrations. One of the biggest trends in modern cake manufacturing is the development of healthier alternatives. Consumers are increasingly looking for reduced sugar, gluten-free, and plant-based cake options that cater to dietary restrictions and health-conscious lifestyles. Factories have adapted by reformulating traditional recipes, replacing refined sugars with natural sweeteners like stevia or monk fruit, and using alternative flours such as almond flour or coconut flour to create gluten-free variations. These formulations require precise adjustments to maintain the desired texture and taste, as the absence of gluten or sugar can affect the structural integrity of cakes. Another emerging trend is the use of functional ingredients to enhance the nutritional profile of cakes. Factories are experimenting with protein-fortified cakes, fiber-rich formulations, and probiotic-infused desserts that offer health benefits beyond traditional indulgence. Cakes with added omega-3 fatty acids, collagen, or antioxidant-rich ingredients appeal to consumers who want to enjoy sweet treats without compromising on wellness goals. Manufacturers use encapsulation technology to protect sensitive nutrients during baking, ensuring that functional ingredients remain effective even after exposure to heat. Sustainability is a growing priority in cake manufacturing, with companies striving to reduce their environmental footprint at every stage of production. Many factories have implemented waste reduction programs that repurpose cake trimmings into new products, such as cake pops, cookie bases, or cereal bar inclusions. Some manufacturers donate surplus cakes to food banks or partner with organizations that distribute baked goods to communities in need. Wastewater treatment systems, energy-efficient baking ovens, and recyclable packaging materials further contribute to sustainability efforts. The shift toward eco-friendly packaging is particularly significant, as traditional plastic cake containers contribute to global plastic waste issues. Factories are exploring biodegradable alternatives, such as plant-based plastics, compostable trays, and paper-based packaging with food-safe coatings. Some manufacturers have developed innovative packaging solutions that extend shelf life without relying on excessive plastic, using breathable film technology that regulates moisture levels to prevent staleness. Smart packaging, which includes QR codes that provide traceability information or freshness indicators that change color based on product age, is also gaining traction in the industry. The future of cake manufacturing is expected to be shaped by advancements in automation, artificial intelligence, and customization technology. AI-powered production lines are already capable of self-adjusting parameters based on real-time data, optimizing mixing, baking, and cooling processes for maximum efficiency. Machine learning algorithms analyze consumer purchasing patterns to predict demand fluctuations, allowing factories to adjust production schedules accordingly. 3D food printing is another exciting development that could revolutionize cake decoration and customization. Some companies are experimenting with 3D printed cake designs, where intricate sugar sculptures, chocolate accents, or even full cake layers are printed layer by layer. This technology opens up new possibilities for personalized cakes, allowing consumers to design unique cake structures that were previously impossible to achieve with traditional decorating techniques. Another potential breakthrough is the use of blockchain technology to improve transparency in the supply chain. By implementing blockchain tracking systems, cake manufacturers can provide consumers with detailed information about ingredient sourcing, production dates, and quality control measures. This level of traceability builds trust with consumers and ensures compliance with food safety regulations, especially in an era where ethical sourcing and ingredient transparency are increasingly important. As the global cake market continues to expand, manufacturers must adapt to diverse consumer preferences across different regions. In some countries, lighter sponge cakes with whipped cream fillings are preferred, while in others, dense and rich chocolate cakes dominate the market. Factories tailor their production lines to accommodate regional tastes, incorporating local ingredients and traditional flavors into their offerings. The rise of e-commerce and direct-to-consumer cake delivery services has further transformed the industry, with many factories now offering online ordering and home delivery options. The large-scale production of apple pies in a factory begins long before the first piece of dough is rolled or the first apple is peeled. The process starts with careful ingredient selection and sourcing, ensuring that only high-quality raw materials are used to maintain consistency in texture, flavor, and appearance. Apples are the most essential component, and factories work with orchards and suppliers to secure varieties that hold their shape during baking. Granny Smith, Honeycrisp, and Golden Delicious are among the most commonly used apple varieties due to their balance of tartness and sweetness, as well as their ability to remain firm when exposed to heat. These apples are harvested at peak ripeness, stored in temperature-controlled environments, and transported in bulk to the manufacturing facility. Before arriving at the factory, apples go through an initial sorting and washing process at agricultural processing plants. They are visually inspected, and any damaged or overly bruised apples are removed. Automated sorting systems use laser scanning and weight sensors to classify apples by size, ensuring uniformity in the final product. Once they reach the pie manufacturing facility, apples are subjected to another round of cleaning, where they pass through water jets, brushes, and food-safe sanitizing solutions to remove any remaining dirt, wax, or pesticide residues. Flour is another key ingredient, forming the base of the pie crust. The type of flour used depends on the desired texture of the crust. Factories often blend different flours to achieve the perfect balance of tenderness and flakiness. Large silos store refined wheat flour, which is sifted and aerated before use. Fat sources, such as butter, vegetable shortening, or margarine, are also prepared in bulk, often stored in temperature-controlled tanks or solid blocks that will later be incorporated into the dough. Sugar, cinnamon, nutmeg, and other spices are pre-measured in precise quantities to ensure flavor consistency across every batch. Before production begins, factory equipment undergoes a rigorous sanitation process. Conveyor belts, mixers, dough sheeters, peeling machines, and baking ovens are all thoroughly cleaned and sterilized to prevent cross-contamination. Strict hygiene protocols are in place, and workers handling ingredients wear protective gloves, hairnets, and sanitized uniforms. automated ingredient dispensers are calibrated to ensure the correct proportions are used, minimizing human error and improving efficiency. The first major step in the pie making process is preparing the apples. Massive apple peeling machines process hundreds of apples per minute, using rotating blades to remove the skin efficiently. Some machines employ steam peeling, which uses high-pressure steam to loosen the skin before it is brushed off, reducing waste and preserving more of the fruit's flesh. After peeling, apples are quickly cored and sliced into uniform pieces. Factories use industrial slicers that cut apples into precise shapes, thin slices for traditional pies, or chunkier pieces for rustic-style pies. Once sliced, apples move along conveyor belts to be treated with an antioxidant solution, preventing browning caused by oxidation. This solution, typically a blend of ascorbic acid, vitamin C, and citric acid, ensures that apples maintain their natural color and freshness throughout the production process. The prepared apple slices are then transported to large mixing vats where they are combined with sugar, spices, and thickening agents such as cornstarch or modified food starch. This ensures that the filling will have the right consistency, preventing it from becoming too runny or too dry during baking. The mixing process is carefully timed to distribute spices evenly without breaking down the apple slices. While the filling is being prepared, the pie crust is mixed and rolled out. In large-scale production, dough preparation is a highly automated process that ensures uniformity across thousands of pies. Ingredients such as flour, fat, water, and salt are combined in massive industrial mixers equipped with precision temperature controls. The temperature of the fat is crucial. If it is too warm, the dough will become overly soft and lose its flaky texture. If it is too cold, it will not incorporate properly. Factories use chilled water and climate-controlled rooms to maintain the ideal dough consistency. Once mixed, the dough is fed into an automated sheeting machine that rolls it to the exact thickness required for pie crusts. The dough is then cut into circular shapes using rotary cutters, ensuring every crust is the perfect size. Some factories employ laminating techniques to create extra layers in the dough, mimicking the effect of handmade flaky pie crusts. Excess dough from the cutting process is collected, reworked, and reintegrated into the next batch to minimize waste. The next step is assembling the pies. Conveyor belts transport the bottom crusts to the filling stations, where the prepared apple mixture is deposited into each pie shell. Factories use volumetric filling machines to ensure that each pie receives the exact amount of filling, preventing overflow or underfilling. The filling must be evenly distributed to prevent uneven baking, and any excess liquid is drained to keep the crust from becoming soggy. Once the filling is in place, the top crust or lattice is added. Factories use automated dough placers to position pre-cut dough circles onto the pies, and crimping machines press the edges together, sealing the filling inside. For lattice-top pies, robotic systems weave strips of dough in an intricate pattern, replicating the handcrafted appearance of traditional home-baked pies. Some factories also produce streusel-topped apple pies, where a crumbly mixture of butter, sugar, and flour is sprinkled over the filling before baking. Before the pies enter the ovens, finishing touches are applied. Some pies receive an egg wash or milk wash to create a glossy, golden brown crust, while others are dusted with cinnamon sugar for added flavor and visual appeal. Venting machines create small slits in the top crust, allowing steam to escape during baking and preventing the filling from bursting through the crust. The baking process is one of the most carefully controlled steps in pie manufacturing. Industrial ovens operate at precisely calibrated temperatures to ensure even baking without drying out the filling or burning the crust. Tunnel ovens, which use conveyor belts to move pies through different heat zones, are the most common in large-scale production. The first zone rapidly heats the pies to set the crust and activate the thickening agents in the filling. The middle zone maintains consistent baking temperatures, allowing the apples to soften while the crust becomes golden and flaky. The final cooling zone gradually reduces the temperature to prevent shrinkage or cracking. Once baked, the pies must be cooled before packaging. Factories use cooling tunnels equipped with controlled airflow systems to bring the pies to room temperature quickly and efficiently. This process is crucial. If pies are packaged while still warm, condensation can form inside the packaging, leading to sogginess or mold growth. Spiral cooling conveyors maximize space efficiency, allowing pies to cool gradually without taking up excessive floor space. Before packaging, each pie undergoes a final round of quality control inspections. Vision inspection systems equipped with high-resolution cameras scan each pie for imperfections such as uneven crusts, filling leakage, or discoloration. Weight sensors confirm that each pie meets precise weight specifications, ensuring consistency in every unit. Random samples are pulled for taste testing and texture analysis, verifying that the crust maintains its flakiness and that the apple filling has the right balance of sweetness and spice. After passing quality checks, pies move on to the packaging stage. Factories use automated wrapping machines that encase each pie in protective film or place them in cardboard boxes with clear plastic windows for visibility. Some pies are packaged individually for single-serve portions, while larger family-sized pies are sealed in airtight containers to preserve freshness. Packaging plays a critical role in maintaining the freshness and structural integrity of apple pies as they move through the supply chain. Once the pies have cooled completely, they are transferred to automated packaging lines where they are placed into protective containers. Factories use a variety of packaging methods depending on the type of pie being produced. Whole pies, designed for retail sale, are often placed in sturdy cardboard boxes with clear plastic windows, allowing consumers to see the product while keeping it protected. The boxes are sealed with tamper-evident closures to ensure food safety and compliance with industry regulations. For frozen apple pies, specialized packaging materials are used to prevent freezer burn and moisture loss. These pies are typically wrapped in airtight plastic film before being placed in cartons designed to withstand low temperatures. Vacuum sealing or modified atmosphere packaging techniques may also be used to remove excess oxygen and extend the shelf life of frozen pies. Factories that produce individual-sized apple pies or snack-sized turnovers use flow wrapping machines to encase each product in a flexible plastic film, preserving freshness while allowing for easy transport and handling. Once packaged, each pie is labeled with key product information, including expiration dates, ingredient lists, nutritional facts, and barcodes for inventory tracking. High-speed labeling machines apply these labels with precision, ensuring that they are aligned correctly and free from wrinkles or misprints. In some cases, additional stickers or promotional labels may be applied to highlight seasonal flavors, limited edition varieties, or special offers. Before shipping, a final round of quality control inspections takes place. Automated vision systems scan each packaged pie for defects such as misaligned labels, improper sealing, or signs of damage. Weight sensors confirm that each pie falls within the specified weight range, and metal detectors or X-ray machines are used to identify any potential foreign objects that may have inadvertently entered the production line. Randomized sampling is conducted, with select pies being opened and tested for taste, texture, and consistency to ensure they meet quality standards. Once cleared for distribution, the pies are packed into larger cartons or cases and stacked onto pallets for shipping. Logistics teams coordinate transportation, ensuring that pies reach their destinations in optimal condition. Refrigerated trucks are used for frozen pies, while shelf-stable varieties are transported under standard conditions. Large-scale manufacturers often supply pies to supermarkets, convenience stores, and food service providers, while some factories also produce private label pies for retailers under store brand names. At retail locations, apple pies are stocked in bakery sections, freezer aisles, or snack food displays, depending on their packaging and storage requirements. Supermarkets and bakeries follow strict inventory rotation practices, ensuring that older products are sold first to minimize waste. Some retailers may also offer in-store customization, allowing customers to purchase plain apple pies and add whipped cream, caramel drizzle, or other toppings before serving. In addition to retail distribution, many apple pie manufacturers supply food service businesses, including restaurants, cafeterias, and catering companies. These establishments often receive bulk shipments of pre-baked or frozen pies that can be reheated and served as needed. Some manufacturers also produce partially baked or par-baked pies, which allow food service providers to finish baking the pies in their own ovens for a freshly baked aroma and texture. As consumer preferences evolve, apple pie manufacturers continue to innovate with new flavors, formats, and dietary options. Gluten-free apple pies, for example, use alternative flours such as rice flour or almond flour to accommodate individuals with gluten sensitivities. Vegan apple pies eliminate butter and eggs, using plant-based substitutes such as coconut oil or flaxseed-based thickeners. Sugar-free and low-calorie apple pies cater to health-conscious consumers, replacing refined sugar with natural sweeteners such as stevia or monk fruit extract. Another growing trend in the apple pie industry is the development of artisanal-style products that mimic the appearance and taste of homemade pies while benefiting from large-scale production efficiency. Factories use specialized techniques to create rustic-style crusts, hand-crimped edges, and uneven lattice patterns that give the impression of being handmade. Some manufacturers also experiment with unique fillings, incorporating ingredients such as caramelized apples, bourbon-infused sauces, or spiced pecans to create gourmet variations. The production process has also seen significant advancements in automation and smart manufacturing technology. Modern pie factories utilize AI-driven production systems that monitor real-time data, adjusting mixing times, baking temperatures, and ingredient ratios automatically to ensure consistent results. Predictive maintenance technology helps prevent equipment breakdowns by analyzing performance patterns and scheduling maintenance before issues arise, reducing downtime and increasing efficiency. Sustainability initiatives are becoming increasingly important in the apple pie manufacturing industry. Many factories are adopting eco-friendly practices, such as sourcing apples from local farms to reduce transportation emissions and investing in renewable energy to power production facilities. Waste reduction programs repurpose pie trimmings and excess dough into secondary products, such as pie crust crumbs used for cheesecakes or repackaged as dessert toppings. Some manufacturers donate surplus pies to food banks, helping to combat food waste while supporting community initiatives. Packaging sustainability is another major focus, with companies seeking alternatives to traditional plastic containers. Biodegradable pie trays made from compostable materials, recycled paperboard cartons, and plant-based plastic wraps are being developed to reduce environmental impact. Some manufacturers are exploring edible packaging concepts where a protective sugar-based glaze can replace plastic wrapping while still keeping the pie fresh. The future of apple pie manufacturing is likely to see continued advancements in customization and convenience. Direct-to-consumer models are emerging, where customers can order personalized apple pies online and have them delivered fresh to their doorsteps. Smart kitchen appliances equipped with pie warming technology may become more common, allowing consumers to heat pre-packaged pies to optimal serving temperature with precision settings. 3D food printing technology is also making its way into the baking industry, with the potential to create intricate pie crust designs, decorative elements, and even printed fruit fillings layered in artistic patterns. Artificial intelligence may play a larger role in recipe development, analyzing consumer preferences and market trends to create innovative new apple pie variations. As demand for nostalgic, comforting desserts remains strong, apple pies continue to be a staple in bakeries, supermarkets, and food service establishments worldwide. The balance between tradition and technological advancement allows manufacturers to produce high-quality apple pies on a large scale while preserving the flavors and textures that consumers love. From ingredient sourcing to packaging innovation, every step of the process is designed to deliver a consistently delicious and visually appealing product. After the pies have been packaged and prepared for distribution, the journey from the production line to the consumer's hands becomes a finely tuned logistical operation. Factory staff and automated systems coordinate to load the packaged apple pies onto pallets, where each case is carefully arranged to prevent shifting during transit. This organization ensures that every pie arrives intact, with its decorative finish and flaky crust preserved. Refrigerated transport is utilized for pies that require controlled temperatures, such as those with delicate cream-based toppings or freshly prepared fruit mixtures, while room temperature varieties are shipped in climate-controlled vehicles to avoid any undesirable temperature fluctuations. Throughout this process, detailed tracking systems monitor the location, temperature, and status of shipments, ensuring that any potential issues can be quickly identified and addressed. Within the distribution centers, a well-structured system of inventory management is employed to maintain the integrity of the pies. Automated scanning and tracking devices help manage stock levels, and storage facilities are organized in a manner that optimizes space, while ensuring that pies are not exposed to excessive light or temperature changes. When orders are processed, computer-controlled systems select the appropriate batches, ensuring that the older stock is distributed first to prevent any waste. In high-demand periods, such as during holidays or seasonal promotions, the system automatically adjusts to accommodate increased volumes, demonstrating the scalability and efficiency of modern industrial food production. Retailers receive the shipments with the assurance that every pie meets strict quality criteria and that the production process adheres to both safety regulations and customer expectations. As consumer trends shift towards healthier and more diverse food options, apple pie manufacturers are continuously refining their recipes and production methods to cater to these evolving demands. One notable trend is the incorporation of organic apples and natural sweeteners. Factories are increasingly sourcing apples from certified organic orchards and experimenting with honey, maple syrup, or agave nectar as alternatives to refined sugars. These innovations are not only designed to meet the nutritional preferences of health-conscious consumers, but also to offer a richer and more nuanced flavor profile. The challenge of maintaining the perfect consistency in the filling while using these alternative ingredients has led to the development of specialized processing techniques. For example, adjustments in the proportions of thickening agents and the precise timing of the mixing process are made to account for the different moisture and sugar levels in organic produce and natural sweeteners. In response to growing concerns over allergen exposure, many apple pie factories have established dedicated production lines for allergen-free products. These production lines are segregated from the main processing areas. It all begins with the careful sourcing and intake of raw chicken, a process that is both biologically sensitive and highly mechanized to maintain consistent quality and food safety. The chickens destined for KFC facilities are selected from specific poultry farms that follow stringent guidelines set by both KFC's corporate standards and local regulatory bodies. These farms raise broiler chickens, a breed specifically developed for rapid growth and high meat yield, particularly in the breast and thigh areas. To ensure consistency in texture and flavor, the birds are typically grown under controlled feeding regimens with strict monitoring of their diet, environment, and health status from hatchery to harvest. Once the birds reach the appropriate weight and age, usually between 5 to 7 weeks, they are transported live in temperature-regulated, well-ventilated trucks to the processing facility. Upon arrival, the birds are unloaded through an automated conveyor system and transferred to a staging area that uses dim lighting and gentle sound cues to keep the animals calm. This pre-processing environment is crucial for maintaining meat quality, as high stress can cause conditions like pale, soft, and exudative meat, or dark, firm, dry meat, which are both unsuitable for KFC's strict quality requirements. The first critical step in the factory is stunning, which is done using controlled atmosphere stunning, a method that introduces carbon dioxide in gradually increasing concentrations to render the chickens unconscious. This technique is widely considered more humane and helps preserve the quality of the meat. Once the birds are unconscious, they move to the next stage, where an automated system makes a precise incision to the neck, ensuring rapid and thorough bleeding. The bleeding process is closely timed and monitored using sensors and timers to maximize the efficiency of blood removal, which is essential not only for meat appearance and shelf life, but also for meeting food safety regulations. Following exsanguination, the birds proceed through a high-capacity scalding tank filled with water heated to approximately 60 degrees Celsius. This stage loosens the feathers by relaxing the collagen in the feather follicles. The duration and temperature are controlled to a fine margin to ensure that the skin is neither overcooked nor damaged. After scalding, the birds are transferred into rotary feather pluckers, drum-shaped machines lined with soft rubber fingers that rotate at high speeds. These fingers remove feathers through a gentle abrasive action. Any residual feathers, particularly around the wings and tail, are removed by additional targeted plucking devices or hand finishing stations, depending on the processing line speed and factory setup. The next step is evisceration, a highly mechanized process involving robotic arms and vision-guided machinery. The system first makes a precise incision along the abdominal cavity before extracting the internal organs. This includes the heart, liver, gizzard, and intestines, which are separated into byproduct streams for different uses or disposal. Each carcass is inspected by high-speed cameras equipped with AI-powered image recognition software to detect any abnormalities such as bruising, discoloration, or contamination. Chickens that fail this inspection are automatically diverted from the production line for further examination or removal. This real-time quality assurance technology helps maintain a consistent and safe supply of chicken for further processing. Now it's time to move on to the chilling process, which is absolutely vital for halting bacterial growth and ensuring a clean transition from slaughter to further cutting and seasoning. KFC factories typically use an immersion chilling method, where eviscerated chickens are conveyed through long stainless steel tanks filled with chlorinated cold water, maintained at around 0 to 4 degrees Celsius. The flow of water is designed in a countercurrent pattern, meaning the cleanest water contacts the most recently added chickens, ensuring optimal hygiene. This step rapidly reduces the internal temperature of the chicken from roughly 40 degrees Celsius to below 4 degrees within an hour, thereby locking in freshness and significantly extending the shelf life of the meat. After chilling, the carcasses proceed to the cutting and portioning stage. This part of the process is perhaps one of the most intricate in the factory. Specialized rotary cutting machines equipped with lasers and 3D scanners assess the size and density of each chicken in real time. Based on this data, programmable robotic blades segment the carcasses into uniform cuts: legs, thighs, wings, breasts, and keels. Each piece is sized to match strict dimensional and weight criteria, which are crucial for ensuring consistent cooking times and presentation across all KFC restaurants worldwide. The system is calibrated to yield the optimal number of each type of piece from every bird, reducing waste and maximizing efficiency. If a cut doesn't meet the precise size range, it is automatically redirected for use in alternative products like tenders or popcorn chicken. The next phase focuses on marination, a process that introduces moisture, flavor, and functional ingredients into the chicken to enhance both taste and texture. Once portioned, the chicken pieces are loaded into massive stainless steel tumblers, each capable of holding hundreds of kilograms of product. Inside the tumbler, a proprietary liquid marinade blend is introduced. While the exact formulation is a closely guarded secret, the marinade typically includes salt, phosphate-based tenderizers, flavoring agents, and sometimes buttermilk solids to create the tender, juicy interior that KFC is known for. The tumbling action lasts anywhere from 15 to 30 minutes, depending on the batch size and desired intensity. And the drum rotates on multiple axes to ensure that every surface of every piece of chicken is exposed to the marinade. This mechanical agitation also helps the meat fibers absorb the liquid more thoroughly, contributing to the product's juiciness even after high temperature frying. But up next comes the breading stage, which is arguably the most iconic part of KFC's production process. After marination, the chicken is gently drained and transferred to the breading stations, where each piece is coated in the proprietary blend of flour and seasoning known famously as the 11 herbs and spices. To replicate the hand-breaded quality that KFC is known for, even at industrial scale, specialized breading drums are used. These drums simulate the hand-tossing action by gently rolling the chicken pieces in the seasoned flour, while pneumatic paddles and vibration systems ensure that every crevice is fully coated. At this point, moisture content is carefully controlled to ensure adhesion without creating clumps or overly moist surfaces, which would ruin the crispy texture during frying. Once breaded, the chicken moves immediately to the par frying or pre-frying stage. This step is critical for setting the breading so it doesn't fall off during full cooking at the restaurant. The breaded pieces are passed through continuous fryers filled with hot oil maintained at temperatures between 170 to 180 degrees Celsius. In this stage, the chicken is fried for a short duration, usually 90 to 120 seconds, just enough to solidify the coating and begin the Maillard reaction, which is responsible for the development of flavor and the golden color. The oil used in this step is filtered and refreshed continuously using an inline oil management system that maintains optimal frying conditions and ensures that the final product is never tainted by burnt residues or off flavors. The partially cooked chicken is then lifted out of the fryer via a conveyor system and deposited onto a draining belt that uses both gravity and air jets to remove excess oil. Now, it's time to transition to the flash freezing process. This is where partially cooked chicken is rapidly frozen to lock in all the flavors, textures, and moisture absorbed during marination and breading. Each piece is conveyed into a spiral freezer or impingement freezer, both of which use sub-zero air blasts or liquid nitrogen vapor to drop the temperature of the chicken from over 60 degrees Celsius to below minus 18 degrees in under 10 minutes. Rapid freezing is crucial to prevent the formation of large ice crystals, which can damage the cellular structure of the meat and result in dryness or texture loss after final cooking. During this process, each piece is also individually quick frozen, which prevents clumping and allows for precise portioning when packaging. The next step in the factory process is the automated packaging of the individually quick frozen, par-fried chicken pieces, a phase that combines high-speed precision machinery with meticulous control over product integrity. Once the chicken emerges from the spiral or impingement freezer, each piece is conveyed to a sophisticated vision inspection system that performs a final quality assurance check. High-resolution cameras and laser scanners examine each piece for uniform breading coverage, appropriate size, and the absence of any structural defects like broken bones or irregular shapes. Pieces that fail this inspection are removed from the line using targeted air jets and routed for rework or disposal, depending on factory protocol. Once the pieces pass inspection, they are conveyed into a portioning station where intelligent weighing and sorting systems group them into standardized sets that align with KFC's iconic bucket meal configurations. These could be 8-piece, 12-piece, or 16-piece configurations, depending on the regional product lineup. Multi-head weighing machines calculate the total weight and count of each portion, ensuring that every pack not only meets visual and compositional standards, but also falls within a narrowly defined weight range for inventory accuracy and consistent customer experience. These grouping systems operate at incredibly high speeds, hundreds of portions per minute, with tolerances as tight as +1 gram. Each portion of chicken pieces is then dropped into a form-fill-seal machine or into pre-formed plastic pouches, depending on the final packaging format. The form-fill-seal machines shape a plastic film into a bag, load it with chicken, flush it with a nitrogen-rich gas to minimize oxygen, and heat seal it in a continuous, uninterrupted process. Modified atmosphere packaging is used here to extend shelf life while preventing freezer burn or flavor degradation. The gas blend, often a mix of nitrogen and carbon dioxide, inhibits microbial growth and oxidation without adding any chemicals or preservatives. After sealing, the packages are labeled with all necessary tracking and compliance information. High-speed thermal transfer printers apply labels that contain lot numbers, plant codes, production timestamps, and freeze dates. These labels also include data matrix barcodes or QR codes used for traceability, allowing KFC's central quality control teams to trace every package back to its exact farm, batch, and processing line in the event of a recall or audit. Automated verification systems scan each label for accuracy and readability. Any incorrectly labeled packages are automatically rejected from the line and placed in a designated review bin for manual inspection. Now it's time to move on to case packing, where multiple individually sealed packs of chicken are grouped into corrugated cardboard boxes, each built to withstand long-distance cold chain transportation. Robotic arms equipped with vacuum suction grippers pick and place the sealed bags into the boxes with extreme precision, ensuring that space is maximized while maintaining the integrity of the chicken. Each case typically holds a specific number of meals or bucket configurations and is marked with a unique identifier. Once filled, the boxes are sealed using automated taping machines and pass through weight verification stations to ensure each box matches the expected load. Once packed, these boxes are stacked onto pallets using robotic palletizers. These robots follow pre-programmed stacking patterns that balance weight and maximize vertical space without compromising stability. Slip sheets and corner boards are often inserted between layers to protect the boxes during transit. Each completed pallet is then shrink wrapped using a rotary arm or turntable stretch wrapper, which encases the entire stack in several layers of industrial plastic film to secure the load for transportation. A final barcode label is applied to each pallet, integrating it into the warehouse management system, which tracks every movement of inventory from production to dispatch. Next comes the crucial cold storage phase. The finished pallets are transferred via automated guided vehicles or high-speed conveyor systems into a massive cold storage facility, maintained at a consistent temperature of -18 degrees Celsius or lower. These storage facilities are designed with energy efficiency and inventory management in mind, often featuring high bay racking systems and vertical lift modules that allow for dense, organized storage. Temperature and humidity are monitored continuously by sensors linked to a centralized control room, where technicians receive alerts if any deviations occur. These warehouses are often equipped with backup generators and emergency protocols to ensure uninterrupted refrigeration in the event of power failures. After sufficient time in cold storage, which may range from a few days to several weeks depending on demand, the frozen chicken pallets are scheduled for distribution. The dispatch process begins with a pick and pack phase, where orders from various KFC regional hubs or franchise warehouses are collated. Advanced logistics software optimizes which pallets to pull based on freshness, production date, and delivery location. Selected pallets are loaded onto refrigerated trailers that maintain a controlled environment throughout the entire journey. These trucks use insulated walls and powerful refrigeration units that can be monitored remotely to ensure temperature compliance from factory to franchise. As these trucks transport the frozen chicken to regional KFC distribution centers or directly to individual restaurants, the cold chain is never broken. The receiving locations are equipped with cold storage facilities of their own, ensuring the chicken remains at safe temperatures until it's needed. At this stage, each restaurant receives a specific allocation based on forecasted customer demand, which is calculated using advanced demand planning software linked to point-of-sale data and regional market trends. The chicken remains sealed until it's ready to be used in the restaurant's kitchen, where the final stages of cooking take place. But now it's time to dive into the heart of the KFC restaurant kitchen, where the transformation from pre-cooked frozen chicken into the hot, crispy, golden brown pieces we all recognize occurs. After thawing in temperature-controlled refrigeration units for a specific number of hours, typically overnight, the chicken is brought to the breading station. Though the chicken was par-fried and breaded at the factory, a second layer of fresh breading is applied in-store to create the distinctive double crunch texture KFC is famous for. This is where the Colonel's proprietary 11 herbs and spices come into play. Each restaurant receives sealed tubs of this secret seasoning blend, pre-measured and tamper-proof. The thawed chicken pieces are first dipped into a cold, seasoned egg wash or a specialized batter mix, depending on the region. Then, they are placed into large breading bins containing the flour and spice mixture. Trained team members follow a specific press and fold technique, which involves pressing the flour onto the surface of the chicken and folding it multiple times to ensure full adhesion and the formation of the characteristic craggy, crispy coating. Each piece is then gently shaken to remove excess breading and laid out on wire racks to rest before frying. This resting period is short but essential. It allows the coating to set and adhere to the surface of the meat, reducing slippage during frying. Next, the chicken is placed into large open fryers filled with high-stability frying oil, often a soybean or canola blend, optimized for high temperatures and neutral taste. The fryers are preheated to exact temperatures, typically around 170 to 180 degrees Celsius, and the chicken is cooked under pressure for a controlled duration. KFC's use of pressure fryers is a distinctive element of its cooking process. The pressure cooking not only reduces cooking time, but also seals in moisture, ensuring the chicken remains juicy while achieving a perfectly crispy exterior. Sensors inside the fryer monitor oil temperature, pressure levels, and cooking duration down to the second. Once the timer signals completion, the fryer basket lifts automatically and the cooked chicken is removed using heat-safe tools to ensure safety and hygiene. After frying, the chicken is transferred to heated holding cabinets that maintain a precise internal temperature, typically around 60 to 65 degrees Celsius, for a limited time, usually no longer than 90 minutes, to ensure optimal freshness and food safety. These cabinets are fitted with internal timers and alert systems to prompt kitchen staff when a batch is nearing the end of its holding time. Any product not sold within this window is discarded according to food safety protocols to maintain KFC standards. Now that the chicken is hot, crisp, and ready, it's portioned into the familiar red and white striped buckets. Each bucket is made from food-grade, grease-resistant cardboard, printed with high-resolution branding that remains vibrant, even under heat and oil exposure. The buckets are assembled on-site from flat pack form using pop and lock mechanisms and lined with waxed paper liners. The kitchen crew follows strict guidelines when arranging the pieces inside each bucket, ensuring an appealing visual mix of drums, thighs, wings, and breasts. The buckets are then sealed with fitted plastic or cardboard lids to retain heat and are either handed to walk-in customers or packed into thermal delivery bags for transport. The final stretch of the production process involves a complex web of quality assurance protocols, food safety audits, sustainability initiatives, and continual technological improvements, all of which are critical to ensuring that every KFC fried chicken bucket, whether purchased in Tokyo, New York, or Johannesburg, meets the same high standard of taste, appearance, and food safety. These behind-the-scenes systems may not be visible to the end consumer, but they represent the foundation of KFC's global manufacturing and supply chain model. One of the most rigorous systems in place is the Hazard Analysis and Critical Control Points, or HACCP, framework. This is applied across all phases of the production lifecycle, from live animal handling at the poultry farms to final packaging at the restaurant level. Every critical control point is identified, monitored, and logged digitally. For example, in the chilling process, sensors verify that the internal temperature of chicken pieces drops to below 4 degrees Celsius within a very specific time frame. If any batch fails to meet that requirement, the system will automatically flag the anomaly, prevent further processing, and isolate the affected lot until a manual inspection is completed. These digital controls are complemented by human oversight. Trained quality control technicians regularly inspect samples at random, visually assessing breeding adhesion, meat color, texture, and aroma. At the plant level, sanitation is treated as a mission-critical activity. Every line, blade, and conveyor is cleaned on a strict schedule using a validated multi-step process that includes rinsing, application of food-grade alkaline and acidic detergents, hot water sanitizing, and ATP testing to detect any microbial residues. Cleaning in place systems are used in closed-loop systems like marinade blenders and oil filtration units, ensuring deep sanitation without the need for dismantling complex machinery. Swabs are taken from surfaces and air samples collected to detect airborne pathogens, all analyzed in on-site microbiological labs. If even a trace of Listeria, Salmonella, or E. coli is detected, entire zones of the plant are shut down and sanitized before production can resume. In parallel to these food safety systems, sensory panels and culinary scientists at centralized R&D hubs conduct organoleptic tests to ensure product consistency. These tests assess everything from the crunch of the breading to the juiciness of the meat and the aroma released when the bucket is first opened. Chicken from multiple plants is cooked and compared side by side in blind taste tests to identify deviations in flavor or texture. If a factory's output strays from the baseline profile, its formulations and techniques are reviewed. In some cases, regional adaptations are permitted. For instance, a slightly spicier breading formula in Southeast Asia, or a less salty blend in Scandinavian markets. But these must be approved through corporate sensory panels and extensive pilot runs. Now it's time to take a look at how traceability and supply chain visibility are achieved at scale. Every piece of chicken can be traced through a blockchain-based system that logs data from farm to fryer. RFID tags and barcode labels track each pallet, batch, and case throughout its journey. When a truck departs a cold storage warehouse, its GPS location is monitored in real time, and its refrigeration status is transmitted back to the operations center every 5 minutes. If a delivery truck's temperature rises above the acceptable range for more than 10 minutes, alerts are sent automatically, and corrective actions are triggered, either rerouting to a nearby cold facility or discarding the load, depending on the severity of the excursion. Once the product reaches the restaurant, the store-level staff become the final link in the quality chain. Every team member is trained not just in food preparation, but in safe handling and equipment calibration. They measure oil temperatures with infrared thermometers before every cooking cycle, check holding cabinet thermostats each hour, and perform timed inventory rotations to prevent expired stock from being used. Any discrepancies are flagged in a digital checklist that is reviewed daily by shift supervisors and weekly by regional managers. Corporate auditors also perform unannounced inspections using checklists derived from international food safety certifications such as ISO 22000 and BRC Global Standards. But up next is a growing area of emphasis for KFC's manufacturing process: sustainability. As environmental concerns increasingly shape consumer expectations and regulatory policy, KFC and its supply chain partners have invested heavily in reducing their environmental impact without compromising efficiency or food safety. For instance, many factories now operate on hybrid energy models that integrate solar or wind power into the grid supply. Heat exchangers capture and recycle waste heat from fryers and ovens to preheat water for cleaning cycles. Water treatment plants have been installed adjacent to major facilities to purify and reuse water from scalding tanks and chilling baths, thereby reducing freshwater consumption by up to 60%. Waste management is another cornerstone of sustainable operations. Offcuts, bones, and organ meats removed during the evisceration process are rendered into protein meal for use in animal feed or fertilizer. Oil used during the par-frying phase is filtered multiple times and eventually recycled through third-party processes into biodiesel or industrial lubricants. Even the breading flour that falls off during coating is collected, sifted, and reused within the same batch cycle if it remains uncontaminated thanks to high-speed sifters and air classification systems. Packaging materials are continuously redesigned to reduce plastic use, and many regional markets have adopted compostable or recyclable buckets made from sugarcane fiber or recycled cardboard. Now let's touch on automation and the future of food manufacturing. KFC's supply chain continues to push the boundaries of factory automation. Smart robotics now handle everything from chicken loading and cutting to box folding and pallet stacking. Machine learning algorithms analyze yield patterns, worker performance, and maintenance schedules to optimize output while minimizing downtime. Vision systems are paired with artificial intelligence to assess product quality in real time, not just based on weight and shape, but also by identifying anomalies invisible to the human eye, such as microfractures or uneven breading density. One of the most promising developments is the integration of digital twins, virtual replicas of entire production lines that allow engineers to test modifications in real time before applying them in physical factories. If a new breeding formula is under development, it can be modeled digitally to predict how it will behave under tumbling, par-frying, and freezing conditions. These simulations save weeks of trial and error testing and reduce waste. Some facilities even employ predictive maintenance systems powered by sensors embedded in critical equipment. These sensors monitor vibration, temperature, and pressure, allowing for preemptive repairs before machinery fails, ensuring smooth operations and uninterrupted chicken production. KFC has also begun exploring vertical integration of its logistics chain. In some regions, specially designed micro-factories are situated closer to major urban centers, reducing transit time and carbon emissions. These micro-factories handle final stage breading and par-frying, enabling fresher product delivery and enhanced responsiveness to demand fluctuations. Combined with real-time sales analytics from thousands of KFC restaurants, these decentralized production nodes can respond dynamically, ramping up or down based on foot traffic, promotions, or seasonality.